Thanks so much for the opportunity to share with you today some of the work I've been doing, thinking about this unusual swing, or how unusual was this swing, kind of from bust to deluge of the North American monsoon between 2020 and 2021. My name's Ariana. I'm a new assistant professor at Dartmouth College, and I've been working on this work with a dear colleague and friend, Jorge Garcia Franco, who's an assistant professor at UNAM. Okay, so some of you are already probably familiar with this, but the North American monsoon makes up about 50 to 80% of total annual rainfall in the US Southwest and Northwestern Mexico. Here I'm just showing a June through September total precipitation map for this averaged over some climatology. So we get these large amounts of precipitation across the mountain range here in Western Mexico that kind of creeps up and makes its way into the Southwest US. Here I'm just showing the monsoon index calculated as the precipitation to fall during the monsoon months divided by that annual total precipitation. And then here's just a time series showing the kind of south, center, and north regions, so that are boxed here. So just breaking out the annual climatology of rainfall for each of these periods. And so as we can see reflected in the maps, right, the northern region gets the kind of very subtle monsoon signature. And then as you go further south, of course, there's an increase in that rainfall. And so I'm going to focus mostly on this northern region here, which is, kind of at the international border and encompassing much of that kind of core, the core US part of the region that gets the rainfall in that Arizona and New Mexico region. Okay, so here I'm just showing a couple of plots using the NOAA monthly US climate gridded data set and ClimGrid, showing the 2002 to 2019 mean rainfall, and then showing the 2020 period versus that 2021 period. And the takeaway here, right, is just to show that in 2020, there was little to no monsoon rainfall that occurred, especially across much of Arizona, compared to this 2021 period where we had this real resurgence in the monsoon rainfall. And then we can also show this as the time series and show just how much these 2 years really stood out. So here we're just looking at the data from 1901 to about 2024. And you can see, of course, there's a lot of year-to-year variability in the rainfall. There hasn't really been a huge trend over these last several decades, but you could see that, again, this is just focusing on the northern monsoon region. We had this 2020 year, which stood out, which was record-breaking in our records going back to 1890, followed by this 2021 period, which really stood out. And then it looked like there was this dry bit again in 2022 or 2023 that I haven't looked at much yet, but I'm interested in. Okay, here's just a figure from that I got from the NOAA website from their kind of 2020 monsoon review, just showing the percent of average precipitation from June 15th to the end of September in 2020. So you can see that it was incredibly dry. This is mostly focused in over Arizona and New Mexico. And so some of the factors that played a role in these weather patterns that culminated in this dry monsoon was a very strong monsoon ridge that suppressed thunderstorm activity. There were also these unusually strong northerly winds, low levels of moisture in the region, in part due to the wind patterns and the high. And then it's also worth noting this was a very high record-breaking fire year in 2020. So there was a thick layer of smoke for much of the year over this region, which, as we know, can act to suppress rainfall. Then on the other hand, like I said, 2021 saw one of the wetter monsoons. And now again, this is just a figure I grabbed from NOAA showing the June through September 2021 rainfalls as standardized anomalies, where we can see that this southern region of Arizona was experiencing this very wet monsoon. And again, just some of the factors that played a role in these patterns to give us the wettest monsoon. So we had a monsoon high that developed quite quickly and was in the right location this year compared to 2020, where it was too strong and not quite in the right location. There's some evidence that this was potentially linked to the Arctic Oscillation. We also had more favorable winds this year. There was a lot of moisture in the region. And although it was another high fire year, we didn't have that same kind of thick layer of smoke that hung around for most of the year. Okay, and another reason that I'm focusing on this northern monsoon region, other than I had written up some of this work as a proposal for NOAA, so I wanted to focus on the US region, but also this northern region just has kind of this highest volatility or this highest year-to-year variability. So here all I'm showing is for these three different regions, the north kind of center and southern region. This is just showing the difference in the year-to-year rainfall divided by the mean. So we can see that the northern NAM region stands out as having this kind of largest year-to-year variability, also making it interesting to look at this, this question. Okay, so getting to the question I posed, how unusual were these anomalous North American monsoon years across models? And so to do that, I'm comparing observations from CREW, the Climatic Research Unit product, to the MESACLIP product, right? So 10 members at 1/4 degree atmospheric resolution, the CESM2 large ensemble, so looking at 100 members at a 1 degree resolution, and then the CAM6 global ocean, global atmosphere models, 10 members, 1 degree resolution, run thanks to this group. So thank you. Okay, so I want to start with the observed anomalies in this region, and how I'm presenting these results is have the total monsoon rainfall for the season and then split out by month to look at what was going on for each month. And this is just the precipitation anomalies for each of the years in the observations. So starting from, I think this was 1920 onwards. And so we can see that there's some, it was cool to see the variability in terms of what each of the months look like. And then just wanted to point out, right, so for 2020, I've highlighted this now in this red star. Each of the months were relatively dry versus if we look at 2021, June, August, and September were around average. September was even below average. And so it was really that July month that led to that record breaking wet monsoon. And then now we can add the model data on top of this. And so these are all the same, just kind of where I'm starring is whether or not I'm talking about the 2020 or 2021 year. And so we have the MESACLIP CESM high res in this kind of yellow. The purple is the large ensemble, and then the orange is the 10-member CAM6 GOGA runs. And so the first thing, the first question, right, was, are these models able to simulate these extreme years? And on average, yes, the models are able to capture that year-to-year variability really clearly. And one thing that I thought was interesting was that on average, it looks like the high-res MESACLIP are capturing that year-to-year variability of the monsoon better, especially thinking about the full season, whereas the large ensemble has a much larger spread, potentially as a function of the horizontal resolution. But I'd like to do some more statistical analyses to do some bootstrapping, and so that we're comparing, right, because we're comparing 10 members versus 100 members here. So to be more fair, to do a better analysis of that. And then now again, kind of the same background, but just now highlighting this 2021 year. And you can see that it was quite wet. And for some of the months, the models were unable to, or it's definitely at the tail end, but overall the models can kind of capture that for the variability, right? And like I said, for this year, it was kind of an average year for August and September, and the large ensemble suggests these really anomalous years are possible. Okay, so how unusual was the swing? So now we're just looking at this volatility metric, so the difference between each year and the previous year divided by the average. And so here's 2020 to 2021 in observations. So it stands out as quite extreme. And then you can see now, thinking about this swing, we are kind of at the tail end of these model distributions, but not necessarily outside of the range of what would be possible in terms of this large ensemble. But yes, definitely quite extreme. Okay, so these anomalous years were unusual in the context of our observational records, but not necessarily across all of the CESM and CAM6 experiments. The anomalous years do lie within, even if towards the tails of the modeled anomalies. And we haven't yet explored the drivers and potential predictability of these two extreme years, which are the next steps that I'm really excited for and would love any feedback on. And one of those things is thinking about the role of sea surface temperatures, right? So these were both La Nina years, but there were some definitely some subtle differences in terms of what was going on more in that Northeast Pacific region and what's going on in the Gulf of California region. And I think these are just some of my next steps, thinking about a more robust analysis of the monsoon precipitation statistics in these models, thinking about fit for purpose, looking for model analogs for these 2 years of interest, thinking about the projections in terms of this kind of monsoon whiplash, if you will, and exploring the predictability of these years. And with that, I'll take any questions. Thanks so much.
Thank you. Yeah, we can have one question.
So you compared the variability between the model and the observations. I'm wondering about the mean. You could imagine that more variance would come along with a greater mean, and whether the low res has a bias in that regard.
That's not something I've looked at yet, but definitely something I will. Thanks.
Okay.
Yeah.
Thank you.
I think we have quite a lot of time, right? Because we're ahead. Or
I don't know whether Paul is here or not.
Our speaker didn't.
yeah, he's not shown up, so we can do more than one question.
I'm just wondering if we can expand the size. Of the
Yeah.
size. Say the same thing. It's like an eye test picture. Yeah. Still no Paul in the room.
Do you have a other question? Okay, if not, let's move on to the next talk. We'll begin by Robert. Thank you.
Thank you.
Robert, are you ready?
Hi. Yeah, can you hear me?
Yes.
Great. Let me share my screen. There we go. Okay, that's working. Great.
We can still see your Google Meet, but yeah.
Yeah, hang on. I'm trying to figure out how to.
Yeah,
Okay, good.
I think that's okay.
Hi everyone. Yeah, so I'm a PhD student at the University of Oxford. I'm working with Timberlings and also Isla. And yeah, my PhD is mainly about understanding dynamic and thermodynamic precipitation changes. We've got to focus on Mediterranean type climates, but in this talk, I sort of just want to talk about the different methods to separate them and essentially the pros and cons of each. So yeah, so these are the 5 Mediterranean type climates that are often sort of studied together. But in this one, I just want to focus on central Chile and use it as a case study for understanding how different methods of separating dynamic and thermodynamic trends can give similar or different results. But the motivation behind this is across all of these Mediterranean type climates, we've seen a really strong decrease in the wintertime precipitation. So I'm showing here data from CRU, so the same thing that Ariana just showed, but this green sort of line is the 10-year rolling average of the wintertime precipitation. And these are the 5 Mediterranean type climates. And you can see that in all of the regions, we're essentially at the bottom or exceeding sort of 20th century variability. And there's been quite a strong decline over the satellite era. And although I'm just showing CRU here, this is true in basically every observational data set I've looked at, and in ERA 5 and JRA 3Q to different extents. So we have very high confidence that this is occurring, and we want to understand why. So one way of separating the sort of dynamic and thermodynamic trends is constructed circulation analogs, which I think some of you might be familiar with. But I'm going to go into a bit of detail about how it works, because I think there are some assumptions that are made that might not be valid. So the way it works is essentially you're trying to figure out the effect of sea level pressure on a target variable. So here, precipitation. So you take a target month. So in this top, I don't know if you can see my mouse, but in the top right box here, I've got July 2021 in central Chile. And you can see this is dominated by high pressure to the west and low pressure to the south. And it's also associated with a negative precipitation anomaly in the same region. And what we do is we find a set of analog months. So here's another one, which is August 2022. And it looks quite similar to the target month of July 2021. And we regress all our 50 analog months on the target month to create a set of sort of weights, beta I, which we can use to reconstruct the target month pressure if we want to. But what we want these weights for is to apply them to the precipitation fields for those analog months as well, and then recreate the precipitation anomaly that we expect from the analogs or from this circulation pattern. And so we essentially will get a dynamic anomaly, and then the target, or the sort of actual anomaly minus the dynamic anomaly, would be as residual contributions to the precipitation. And I think it's best to think about this as the precipitation that we expect from the sea level pressure and a residual, not strictly dynamic and thermodynamic. If you do this for every month as the target month, you then can get a time series of dynamic and residual precipitation and then calculate a trend. So here I'm showing precipitation with CRU again for Chile over the satellite era, and we see about 80% of the trend here is dynamic. We have a reasonably strong, although not anywhere near as strong as the dynamic, residual trend, giving us a very strong total trend in these regions. But you can also use a totally different method to do this. You could use the moisture budget analysis, and this basically relies on the equation for conservation of water vapor. And there is a sort of moisture convergence term, there should be a minus sign here, sorry about that, where you have changes in Q and changes in U, both leading to convergence or changes potentially in the convergence of moisture, which will lead to changes in evaporation minus precipitation. And you can split this moisture convergence up into two changing, or two types of change. So you can have changes in Q and changes in U. So what I've done here is do a sort of Reynolds decomposition of both Q and U and split them up into the climatological value, the monthly anomaly, and then the 6-hourly sub-monthly anomaly from that monthly anomaly. And when you combine all these terms and do the decomposition, you end up with 9 terms. But one of them is essentially only related to the change in the monthly Q anomaly. And this is often called thermodynamic. However, is this the same as the thermodynamic change you get in precipitation? Well, not necessarily, because we've also got evaporation to consider here. However, we don't have to use precipitation as our target field for the circulation analogs. We could just use this moisture convergence directly. So what I'm about to show is a comparison of the moisture convergence from the decomposition and also from the circulation analogs. So on the right, I have it for the circulation analogs, and like the precipitation, it looks really similar. So we have a strong dynamic trend and a weaker but non-zero residual trend of about 13% of the total. On the left, we have the 9 terms from the decomposition. 5 of them are 0, which is sort of by construction of the way we set this up. And we find that this thermodynamic term, which is D here, is about 14% of the total. So it sort of seems like, at least in observations, they're quite similar. Both methods will give the same result, which is encouraging. So we looked at a large ensemble to see if this was true across multiple members. So we used 100 members of the CSM2 large ensemble and 92 from the pre-industrial control over the same satellite era. And what we found is that actually both methods normally give very different answers, and that the reanalyses just happen to be quite similar. So on the y-axis here, I've plotted the residual trend from the analogs, and on the x-axis here, I've plotted this trend in specific humidity monthly anomaly term from the moisture budget. And I think the most striking thing is you can see that there are quite a few members which have a different sign for the overall thermodynamic trend, depending on the method that you use. In fact, so this dotted line is the one-to-one line. So if they were exactly the same, they would lie along this line. So the average deviation from this one-to-one line is as big as the average trend predicted by these methods across the large ensemble. So there's a really big spread, and this only gets worse when you look at long time periods. So if you just look at the right-hand plot, the light red, sort of pinkish trends are what you get from applying the circulation anomaly and finding the residual over the whole 120-year period from 1980 to 2100 in the CSM2 large ensemble. And you can see there's quite a big spread, and the mean trend is about minus 0.3 millimeters per month per year. If you look at the moisture budget, you see a much tighter distribution, and it's much stronger. So we wanted to sort of understand why they're different. And it essentially comes down to the fact that both of these methods are somewhat contaminated by dynamic trends. So what we're really after is this change in Q due to the Clausius-Clapeyron sort of effect. And this change in humidity will lead to a change in the monthly anomalies of Q. And it also will show up in the residual analogs term. So what we ideally have is something like this, where the residual analogs term and this monthly anomaly both capture the changes in Q. But the issue is that changes in Q can occur from other reasons, specifically changes in the circulation. So changes in the circulation will cause a change in Q. It doesn't need to be coupled with a U monthly change as well to show up in this term. And this change in Q, because it's expected from the circulation change does not show up in the residual analogues term, but instead shows up in the dynamic analogues term. So does that mean that the residual analogues term is a better estimate of this true thermodynamic trend? Probably not. Firstly, if I go back, there's this enormous spread that I think we're still trying to figure out. But also, any change in the amount of sub-monthly variability of the precipitation or the moisture convergence that's explained by the monthly mean SLP will show up in this residual term too. So if somehow the statistics of the sort of precipitation variability are becoming non-stationary, this will lead to a trend that isn't explained by your analogues, and therefore this trend will show up in the residual term. So I guess the take-home message is just that neither of these methods are perfect in capturing thermodynamic rainfall trends, and they can give you very different estimates over longer time periods especially. And so I guess future plans are to try and figure out a way to refine our estimate of thermodynamic change by combining them somehow, something along those lines. And yeah, with that, I'll open up for questions. Thank you.
Any question?
Nice talk. From my understanding, this analog method is widely used. And so is this implying that this discrepancy or this problematic aspect is really most pronounced in these Mediterranean regions, or does this hold generally for use of this method?
So I think this is something I want to look into more. I haven't done a lot looking at other regions yet. I think, yeah, the analog method is pretty widely used. I do think there's been a bit of a shift away from calling the residual thermodynamic recently, which is good. But yeah, so looking sort of more widely to see where the discrepancies align the most is something I'm keen to do.
I guess I'm just asking this because I know you've looked at it and I've forgotten the answer, but can you remind us, like, what happens when you do the moisture budget and you just do a kind of Clausius-Clapeyron scaling estimate of the humidity instead of the actual change in humidity?
It ends up looking better. Sort of more similar to the analogs, at least.
Okay.
But I'm pretty sure there's still a much tighter distribution from the moisture budget method than there is from the analogs. So this big variability is still a bit of a puzzle, I think.
Yeah.
Would you mind going back to those box plots?
Yeah. Sorry, I know you can sort of see yourself here. Yeah, this one.
Yeah, and because I wanted to ask about the variability, if you think that's, yeah, if you had any theories for why there was such a difference in variability here between the methods, and could you remind me which method is which again on these?
Yeah, so the darker colors are the moisture budget.
Okay.
I have a theory, which is that if you have some analog that's very, very close to your target month, it would lead to a really high beta coefficient that would essentially dominate your regression. So I know that normally this method, and what I've done here is you sort of resample it a whole bunch of times to avoid that. But I wonder whether if you're resampling, if you've got 50 analogs and you're resampling down to 30, that still leaves the 60% chance that you're picking this potentially problematic analog month. I'm not beyond that. I'm not really sure.
Yeah, I'm not that familiar with this, but just thinking it might be interesting to construct like end member examples where you have perfect analogs and like absolutely awful analogs and trying to understand how those affect the analog method. Or again, I don't know exactly how we construct that, but trying to explore the statistical side of the analogs might be interesting with some pathological examples.
Yeah, it definitely, the method gets worse if you consider worse analogs. So I think there's a fairly arbitrary threshold at like the number that you set. If you have too few analogs, the issues with that, I guess, are obvious in that you're not capturing enough. You're not going to be able to recreate your target pressure very well. But if you have too many analogs, you end up sort of smoothing it out and not finding any non-linearities in the way that pressure relates to precipitation or whatever you're looking at. So I agree that the sort of stats need probably a closer look too.
Are you seeing the message in the chat there? Aren't you by construction dealing with a highly collinear set of predictors in your regression?
Yes, you are, which is, I guess, a reason for getting those really high beta coefficients, which I was talking about earlier. There have been other sort of dynamical adjustment procedures where you look at sort of the EOFs and reconstruct your sort of your target month pressure based as a linear combination of the EOFs, but it doesn't tend to work very well because you can't get close enough to your to the reconstruction without essentially just introducing loads of noise into the system by considering like the 10th EOF or something like that. There was a paper, I think, by Sebastian Sippel in 2019 where they found that of all these dynamical adjustment methods, this was the best, at least for precipitation.
Should we discuss what's in the chat, or is it?
No, I'm just chatting with
Okay. I don't know. I feel like the spread could somehow be, because like depend on how big the circulation in Q is variance compared to the actual thermodynamic driven Q. Like in the moisture budget, you just have the delta Q in there. That's your source of variance. Whereas in the analog method, you have how do those analogs affect Q? Yeah.
Yeah, that's true.
There's lots of things going in the chat, which maybe we can.
So sorry, Claudia and I were just discussing different regression approaches that might solve this, but maybe Sebastian discussed that in their study, just different ways to handle regression.
Yeah. So ridge regression has been used, and I think a really recent paper has just come out comparing ridge regression and analogs, and finds that ridge regression performs better than analogs for temperature trends, I think, over Europe over the satellite era. So ridge regression would help, and I might look at that too and compare it and see how it affects things.
Okay, thank you. Let's move on to the next talk. Will be given by Mengqi Jia. Also remote. Is Mengqi, are you there?
I got an email from Elizabeth saying that
Oh yeah,
there's an emergency.
this one is canceled.
Oh,
Yeah.
So we were going to shift up. We're going to be finished really early.
okay.
So now
Now
it's
then move on to the John, Nicholas. John, are you there?
does not look to be there. Let me just check. He's not in the chemistry one.
Okay.
I did write to him to say that we had a cancellation and to join early. So I'll write back to him because I don't see Jerry either.
Jerry's
I
here.
responded.
Thank you. Sorry.
So
Maybe. Yeah, maybe Jerry, do you want to go next? And you'll follow up with the other speakers?
okay.
You being the first in-person speaker.
Yeah, I don't know. This. Let's put it on the desktop. And I guess we need to share this. Yep. I'll just do the entire screen, I guess. Oh, I think there's some security thing that's not letting us. So it would let us share a Chrome tab, but not a window. That's weird. I bet it's an administrator password too.
I might be able to set that in mind.
Yeah. I can also do it. Have the folder, Elizabeth.
Got it, Ira.
Oh, okay.
Yes, I do. Do you need me to share?
I think Nathan has it here.
Thanks, Nathan.
Yeah, sorry about that.
Right, just steal your laptop. Just use the pointer. Here.
Yeah, that's good.
Okay, so we acknowledge collaborators on this work. And we've kind of working this for a couple of years now. We kind of ended up getting a paper. It was published a few months ago in NPJ Climate and Atmospheric Science. It's over there on the right. And this part of, I'm going to present the part of the work that's kind of the end of this, which is we looked in the first part, we looked at how the Australian wildfire smoke kind of helped trigger the year of the triple dip La Nina starting in 2020. And then I'm going to talk about kind of things that were maintaining it and then what ended it. And this relates to how these events end in our initialized hindcast, as well as how the triple dip La Nina actually ended in the observed system. So the smoke from the Australian bushfires in 2019-2020 has been shown to contribute to the initiation of triple dip La Nina. But I'm going to say a little bit about what maintained it and what ended it. And so we did two sets of initialized hindcasts with CSM2 and E3SM version 2, both were initialized in August 2019. We initially ran these for 3 years, July 2022, and then for reasons I'll explain later, we extended those to March 2023. 30 and some of each. We're going to look at annual averages August to July. And of course, there's an aerosol scheme where the smoke can affect the cloud brightness off the coast of South America. One set is a standard SMILE or no smoke simulation, 2 models without the bushfire previously. And the other set, we added the Australian bushfire smoke conditions from this GFED observational database. We call these the smoke experiments. And the differences between these two, the smoke minus no smoke shows only the effects of the wildfire smoke. So in other words, how the trajectory of these simulations changed when we added the wildfire smoke. Another attractive feature of this methodology is by performing differences of these parallel initialized experiments, by doing the differences, we can remove model drift, which is a very nice feature. So just to show how the smoke minus no smoke evolution occurred, the CSM is in the left column, E3SM on the right. Year 1 on the top, year 2 in the middle, year 3 on the bottom, and the observations for a time period during this La Nina in the bottom there. You can see in both models, starting in years 1, you see a kind of a weak La Nina signal, mostly in the eastern Pacific, and then in both models, the La Nina SST anomalies, negative SST anomalies, those blue colors in the Pacific, actually spread to the west and intensified. And you can see the CSM has about twice the amplitude of the anomalies in E3SM, and this is kind of a consistent thing that ran through all these experiments, but they're both getting the same sense, the reaction, this wildfire smoke. So just to review, it's kind of early work in the top of the onset. The argument is that the smoke crosses the Pacific, gets over there to the Eastern Pacific, interacts with the clouds, stratus clouds off the coast of South America. The reason the smoke can get across the Pacific is it's emitted in the subtropics, so there's not a whole lot of rain out, so it's able to survive a trip all the way across the Pacific. The smoke brightens the clouds. That means less solar getting to the surface. That means the sea surface temperatures cool, and those cool SSTs get up in the Eastern Pacific, and then Brittany's feedbacks take over and expand the whole system. And the bottom panel there is this kind of mature La Nina kind of system with the stronger trades pushing the warmer water over toward the maritime continent, where that warmer water then fuels stronger convection and precipitation. That means stronger vertical motion, which means a stronger water circulation, which means you have stronger descent on the eastern leg of the water circulation over there in the subtropical Pacific. That strengthens the subtropical high. That means the trade winds get stronger. It means you get even stronger trade winds upwelling polar water, and it just keeps going. It's a really nice positive feedback through this Brittany's feedback. There's also some off-control ocean heat content anomalies that I'm not going to talk about today that they're a part of this as well. So you can imagine that once this gets going, this set of couple of feedbacks, it could go indefinitely until something stops it. And so that's what I'm going to be talking about today, is what can stop this, this kind of set of coupled processes. And that's the question I'm going to ask. So we were wondering, when we get to between year 2 and year 3, maybe some ensemble members would kind of weaken. The La Nina wouldn't be as strong. Some ensemble members would be stronger with La Nina. So we said, well, let's look at the spread across the ensemble members to see if, if we can see anything going on that could give us some ideas to what was going to end this event. It turned out, and we expected that we were going to see mostly La Nina kind of responsive, just to see either stronger or weaker. But what we actually saw in this scatter diagram on the top here, where we were plotting Nino 3.4 SST anomalies on the y-axis, and this Brittany's feedback, which is a measure of the average surface wind stress anomalies across the equatorial Pacific. You can see that in the lower quadrant is a La Nina, ongoing La Nina in year 3 with strong Brittany's feedback, but in the upper right-hand quadrant, these are ensemble members that showed an El Nino that developed with weak Brittany's feedback. So it really kind of broke it down into 2 categories, where some of these ensemble members were transitioning not just a weaker La Nina, but actually to an El Nino in the 3rd year. And to give an idea of what that kind of breaks down into this distribution on the bottom, you can see that the 2 models there are the 2 different colors. But there's more ensemble members to the left, which means La Nina. But to the right, on the El Nino side, there are some ensemble members over there as well. Of course, there's more on the La Nina side because the ensemble mean, which we showed earlier, was showing an ensemble mean La Nina. But some of these events are actually transitioning, and those are the ones that are kind of interesting. So, okay, let's take the 5 strongest sustained La Nina events that lasted to 3 years, and the 5 that transition to El Nino, the strongest that transition to El Nino, and composite these and come up with 2 sets of differences. And so this is now from the CSM2. This is now for year 2, or the top 2 panels. And the left column there is these 5 ensemble members had the strong sustained La Nina that lasted 3 years. On the right are the ones that transitioned after year 2 into year 3 to an El Nino event. So if you look at the preconditioning that's going on in year 2 as to what could have contributed to this transition, you can see in this area, this oval here near Hawaii, that the North Pacific Meridional mode starts playing a role. And this is something that Steve pointed out yesterday in this recent paper that just came out that he was a co-author on. The North Pacific Meridional mode is the thing that's really the biggest difference between these 2 sets of simulations. In the right, in the upper right, where the La Nina then transitions to El Nino in the lower right. You can see that the transition occurs to positive SST anomalies in year 3. You can see there's a positive North Pacific meridional mode. In other words, above normal sea surface temperature anomalies coming down from the subtropics into the area near Hawaii and across the Pacific. And in the sustained event on the upper left, you can see a negative North Pacific meridional mode. And that then contributes to keeping the La Nina going into year 3. And that's for CSM. Let's look at E3SM, kind of same story. You can see that area near Hawaii in year 2 is really different between the two models. And the one on the right transitions to El Nino after the positive NPMM, and the one on the left stays as a La Nina with a negative NPMM. Okay, well, that's interesting. So that kind of points to the possible importance of the North Pacific meridional mode in these transitions. So what happens when you get a positive North Pacific meridional mode? On the upper right, these are precipitation anomalies, and as you'd expect, over the warmer sea surface temperatures, you see enhanced precipitation. Those are the red colors, they're positive precipitation anomalies. And in the curtailed events, and then in the sustained events, you see kind of just negative or kind of weak anomalies, precipitation anomalies. And then in E3SM, you see the same kind of thing. In the area of the positive NPMM, you see positive precipitation anomalies, and you don't see those in the sustained precipitation anomalies. So what is happening then is when you start messing around with where the precipitation is occurring in the tropics, we know we start affecting the water circulation, these large-scale east-west circulations. Water circulation from the maritime continent back over the Pacific was a key element in keeping this whole Bjerknes feedback loop going. This part of the water circulation, which could be kind of the northern edge of it, could be something that could disrupt that and cause a transition. So what does that look like in terms of a measure of what we can look at for the kind of an indicator of the water circulation? This is 200 hectopascal velocity potential, which is kind of typically used when you have negative values. You have upper level outflow from strong vertical motion precipitation. It's the tropopause and spreads out, and positive values indicate upper level convergence and subsidence, and that suppresses precipitation. So when you look at this area over near Hawaii, where those white ovals are there in the top row, you can see that there's blue colors there for the anomalous upper level outflow over those stronger precipitation anomalies. And you're seeing over the Western Pacific, or over the maritime continent, you're seeing some upper level convergence. You're actually getting an arm of the water circulation moving back in the other direction, suppressing precipitation over the maritime continent, but in the southern hemisphere, it's staying pretty much the same. So it's like we've broken the water circulation into two parts, and that's going to end up affecting what happens at the surface. Because now, this is now CSM. We're looking at the curtailed events of transition. You see this anomalous low near Hawaii, where the SSTs were warm and we had stronger precipitation, so you get anomalous low pressure. And it's, of course, in the sustained events, the red colors there near Hawaii indicate that the anomalous high pressure is still there. When you look at the other side of the Pacific there over Australia and the maritime continent, on the left, the sustained events, you get anomalous low pressure over the maritime continent and over Australia. On the right, you can see that the dark blue colors are darker there over Australia, so the anomalous low pressure is still really strong. But this suppression of the precipitation over the maritime continent is starting to weaken the anomalous low pressure over the maritime continent. That's setting up an anomalous meridional sea level pressure gradient from stronger sea level pressure anomalies to the south and weaker to the north, which then would induce anomalous westerly winds, which you can barely see the vectors there, but I put a black arrow there to highlight where these anomalous westerly surface winds are occurring. This is due to this kind of asymmetry between these two parts of the water circulation. Once you get those anomalous westerly winds, of course, then you trigger downwelling Kelvin waves, you deepen the thermocline in the east, and you contribute to a transition to an El Nino event. And you see the same kind of thing with E3SM as we saw in CSM. So it just indicates that both models are doing roughly the same thing. Okay, so we submitted this paper. I think Mike McFadden was one of the reviewers. And he said, well, this is all really interesting, but can you relate this more to the actual triple dip La Nina? Because the actual triple dip La Nina started in March of 2020. And the black line here is NINA 3.4 observations. And you can see that the black line goes negative just a little after March 2020. The way we set our experiments up was that we initialized the model in August of 2019 because we wanted to start prior to the Australian wildfire smoke being injected. And so our lead year one kind of overlaps half with the actual year one of the La Nina. So he said, well, have you looked to see how this ended up coming out compared to the actual triple dip La Nina? And you can see what happened there on the right, that this is the observed La Nina 3.4 sea surface temperature anomalies. You see the triple dip La Nina, those blue colors there, basically was shut off by the El Nino event of 2023-2024. Okay, so we extended our experiments out to the March 2023, where the transition occurred in the observations. Interestingly enough, on the ensemble mean now, the CSM, which is the blue line, actually on the ensemble mean, those members transitioned out into El Nino a year prior to what was going on in the E3SM, which then gives an interesting contrast between those sets of ensemble to see why the CSM transitioned out and the E3SM didn't. And that's what we're looking at here. This is the CSM. Now, the top three panels are the ones I showed before, which 3-year La Nina event. You can see now in this extension at the bottom there, the CSM ensemble mean now is transitioned to a El Nino. And you can see there in year 3, there's a positive North Pacific marinal mode near Hawaii that's formed that's contributing to this transition in the ensemble mean of these events. But if you look at the E3SM and you look at that third panel from the top there, you can see it's a negative NPMM, and that contributes to sustaining the La Nina into this extension period in the E3SM. So it's the same kind of theme. It's this NPMM seems to be playing a critical role in these transitions. And this, as this paper that Steve was talking about yesterday indicates, this is kind of going, it's a different idea about how these things transition, because one of the conventional ways these transition is a big MJO event that comes across. You have westerly wind first in the Western Pacific, and that provides the westerly winds that produce the downwelling Kelvin waves. This is a little bit different mechanism. So it's coming through a part of the water circulation that's north of the equator, that's not being affected south of the equator, that sets up this anomalous sea level pressure gradient in the west, and that gives you the anomalous westerly wind anomalies. Okay, what did happen in the observation? So this is now the year before the end of the triple dip La Nina, and if you look at the upper left, that's observed sea surface temperature anomalies. You can see some evidence of a positive NPMM forming there in the year before. The upper right is precipitation anomalies, and as we saw in the model, the red colors there enhanced precipitation over those warmer SSTs, or in the region of the warmer SSTs. In the lower left, you see the lower sea level pressure forming over those the warmer water and the stronger precipitation, and that's actually producing a change in the water circulation north of the equator. And you can see that the meridional sea level pressure gradient in the lower left is staying. The anomalous low is still in place over Australia, but it's weakened somewhat. North of Australia and the maritime continent, you can see these westerly wind anomalies coming in from the Indian Ocean, highlighted there by that solid black arrow. So it looks like a similar set of things happened in the transition out of the triple dip La Nina into the El Nino of 23-24. And this was the transition. This is now the observations for that 23-24 El Nino, and that's was highlighted there in the Nino 3.4 time series. Okay, so just to kind of summarize this, I talked about how the wildfire smoke kind of contributed to starting out this multi-year La Nina event, but then these, in the lower left, these couple of these feedbacks through the water circulation kept going, and something had to happen to make that stop. And what ended up happening in the model simulations that did transition, in the right panel there, you can see that there's a positive NPMM there. Those red colors there are the warmer positive SST anomalies. Lower sea level pressure, and you get this kind of anomalous leg of the water circulation coming back and suppressing precipitation over the maritime continent. That's reducing the magnitude of the negative sea level pressure anomalies there. That sets up this meridional sea level pressure gradient, because the low stays strong over Australia, because you still have that southern part of the water circulation that's working there. And you set up this meridional sea level pressure gradient that contributes to this these westerly wind anomalies that then contributes to the transition to El Nino. So just to summarize, we reviewed that the smoke from the wildfires contributes to the initiation of the multi-year La Nina. The main process that sustained the multi-year event is Variability feedback through the water circulation. And the processes that ended the multi-year event seem to be traced, at least in the models, the two models, and possibly the observations, to the formation of a positive North Pacific meridional mode near Hawaii. And this is this Liang et al. Science Advances paper that Steve was talking about yesterday that also came to that kind of similar conclusion. Thanks.
Do you have any question?
Yeah, thanks, Jerry. That's super cool. Could you go back to the first slides where you do the 5 members from each model?
Yeah. This one?
Or the next one?
Yeah.
So am I interpreting it right that in the E3, or I guess the E3SM ones, that the members had the strongest year 3 La Nina showed an El Nino in year 2?
Okay, so this is a contrast between
Yeah.
CSM's at the top, E3SM.
Yeah.
But they both had this, I mean, when we first started looking at this, okay, you look for what's different between these two, right?
Yeah.
The thing that immediately jumped out was Syria by Hawaii. That's the biggest difference between these two.
Yeah.
And then you say, well, okay, what possible difference can that make? And then you start tracing these couple feedbacks, and that's kind of how we end up with this kind of conclusion.
Yeah, definitely. I guess I'm wondering if in the E3SM, there's also this other story of more of an oscillatory. And so at least in these extreme members of really strong year 3 La Nina.
Yeah, it could be. And I know the John Pasula has a plot that I don't have with me, but showing that the E3SM actually got a pretty strong 23-24 El Nino. So it did transition out of that in the Hindcast predictions. So it just took it a while longer, and the E3SM is just weaker than CSM, but it's got about half the amplitude of ENSO that CSM has. CSM is about twice the amplitude of observations. E3SM is closer to observations for whatever that's worth, because these things are we're in sensitivity experiment land. So you're looking at possible reasons why the CSM is giving a bigger response to E3SM, and that could be it. It's just CSM is more reactive, give you a stronger response to something like these wildfire smoke. But it was reassuring. I mean, usually if you look at one model and you see something, and you look at a second model, you see something totally different. Luckily, both models were showing kind of a similar kind of thing, which is reassuring. Yeah,
Yeah, I guess I was wondering how similar they are. Well, like when you're averaging over all the members, E3SM kind of looks like more of a broad scale tropical cooling. Is there some like metric of whether there's really a La Nina as opposed to like just overall cooling that?
Yeah,
can be
well, I mean,
used to say
so
it's definitely.
yeah, so this is kind of, these are the strongest ones. But of course, if you look at the ensemble mean, I think is what you're talking about.
Yeah.
Yeah, this one.
Yeah.
Yeah, so this definitely is showing kind of a weaker kind of Pacific Basin wide kind of thing. But there's the negative NPMM coming that's still there, and it's already positive in the CSM. But yeah, when you're looking at the individual events, of course, they're all a little bit different. And for sure, the E3SM is weaker. It's pattern and amplitude, but it's kind of going in the right direction. So
Yeah.
that was a good thing, I guess.
Do you see any more prevalence of the positive meridional mode in E3SM that could explain why there's less of a?
Haven't looked at it except in this way where we're just looking at the ensemble mean and then break it down into the 5 strongest on either side. But yeah, there's always these questions about El Nino and how it gets simulated, and I think the biggest thing we thought was probably contributing these differences is just that CSM just is giving bigger ENSO variability, and so you kind of expect to get a bigger response out of something like this. But there could be a lot of other things going on. But I think this NPMM thing, which is like in this Liang paper, and there's of course been literature on this going back into the early 2000s about the NPMM, but nobody quite knows what to make of it because it kind of appears, and there's literature that it propagates through this west feedback. But when you look at these things in the models and even in observations, it just kind of appears. It's not like anything's propagating across. It all of a sudden is all up there all the way across the Pacific, which indicates there's probably affecting the strength of the trades going all the way across, and there's something large scale about it. So I don't know if it's propagating more than it sets up by atmospheric forcing coming from the NPO probably, but then where does that come from? What's forcing that? And so it seems like the jury's still out on how you can figure out what's actually causing this. And they kind of, literature kind of ends up saying, well, it's kind of stochastic. So sometimes you just get this NPO that's in this phase, and then the end of the Meridian mode kind of sets up. But it also appears in literature for ENSO timescale and decadal timescale. So there's a lot of things to this and it probably connects tropical and mid-latitude circulations, which is why it's been more difficult to figure out, I think.
If you go back to the plot show year 1, 2, 3, and I see similar, this one is for the year 1 CSM. There's some similarity with year 3, right? But the positive temperature anomaly seems like a little bit to north. Or
Oh, I mean this.
yeah,
Here, yeah.
so that one is not the meridian mode.
Yeah, it's probably a little bit too far north, but it may have been, and I don't know, it was probably there in the initial state, the initialization probably had it in there. We haven't looked back any further from this, but that'd be an interesting thing to look at, I think. But so and this is typically what happens in La Nina. You get opposite signs, Caesar temperature anomalies kind of to the northwest and southwest, kind of sets up nicely here. Yeah, this first year is kind of interesting because there is some evidence of a positive NPMN, which could have contributed to some of this what was going on in the tropics.
So,
Yep.
but in just having a look at the modes in southern hemisphere, because I think the host here is Australian wildfire, the natural link should be like kind of SPM and
and that the southern hemisphere part was another part of this. There's a southern Pacific meridian mode. There's northern and southern. If you look at the literature, the northern is what we're concentrating on here because the southern hemisphere seems to just set up and stay pretty much the same. So if you got this really big negative, you could say that that's maybe a negative South Pacific meridian mode, but nothing really happens in the southern hemisphere. Most of what's happening to make this transition is occurring in the northern hemisphere with the NPMM. In the southern hemisphere, it gets more complicated as the SPC is involved, and then how that's interacting. That's a big tropical latitude interaction piece of that. What's going on in the South Pacific. That also has a lot to do with what the strength of the subtropical high and the strength of the trades. So you get into a whole different set of kind of coupled processes coming out of the southern hemisphere, which is really interesting. But for this, when we were looking at what's different between these two sets of transition and didn't transition, it was mainly the NPMF.
All right, thank you. Thanks. So our John is online now, I believe. Are you there, John?
Thanks.
super cool.
I'm muted. Yes. Hello.
Oh, okay. Hi. Sorry, our schedule is pretty messed up. So but we can do your talk now if that works.
Yes, that absolutely works. And great stuff. Thank you again for inviting me. Let me see about I have way too many windows. Okay. Share it's right here. Oh no. Doesn't have it says I need, oh shoot, okay. 1 second. I think I need permission to share my screen. 1 second, I'll be right back.
Okay, no worries.
Sorry.
I also could grab it and share it for you if that's
let me take 1 minute and see if I can get it to work on Google Meet. Let me try it in another browser. Be um, okay.
Our schedule has changed quite a bit, just in case you came in for Jerry's talk. We just had it. Yeah,
Yeah, right.
we had a missing speaker the first talk.
All the first speakers of the day must have skipped down. I was sitting in the atmosphere working group and it's the same thing.
Oh, really?
Yeah.
Our first one was, I think, located in Africa, and so I wonder if they just had a time zone confusion.
Yeah. Yeah. This one was someone from Central Europe and I assume it was the same thing. So. Jerry, for all these, like spread of the ensembles for these runs, are they all being started from like completely different initializations?
Small revisions.
Okay. But those are like, I've already set it up and.
Well, at least we're going to be back on schedule.
At the start of the time or the ensemble splitting from the start?
Yeah, they spread out from the start.
Yeah.
But then first one set has the smoke in it, the other set doesn't.
Yeah.
Of course, that's a big forcing, so.
Yeah. Yeah.
You can still see a lot of spread even with the small perturbation.
Yeah.
Again.
That makes sense.
Hello, I'm back.
Hi.
Is sharing working?
Yes, we can see your whole screen.
Okay, perfect.
All
right,
yeah, we just
so-
see the Google Meet kind of little window is in the way, but
Oh, I can hide that. Okay.
looks good.
Now you can see my whole screen?
Yep.
Okay. Apologies for that delay.
Worries.
I'm more used to working with Zoom than with Google Meet, but I'm here to thank you for letting me present these results. I am part of a large international collaboration to address when the climate is going to cross 1.5 degrees. So this talk is about climate nowcasting methods to determine 1.5 degree exceedance. There are over 60 authors listed here. You might be able to spot a few names, but we're all just trying to answer this big question. So how well can we quantify when 1.5 degrees Celsius of global warming has been exceeded? And we just submitted this paper. It's in open review. But if we look at what 1.5 degrees actually means as defined in the Paris Climate Agreement, there's several different parts that are ambiguous. There's 1.5 degrees relative to what? That's the pre-industrial ambiguity. And while there are still some details about whether 1850 really is representative of the pre-industrial climate, we can kind of reach a consensus that 1850 to 1900 is good enough to use as a baseline average within observational climate records. The next question is, what do we actually mean by temperature? And again, while observational products like HADCRUT don't exactly match the global mean air temperature, they also use the ocean surface temperature instead of the 2-meter air temperature, we can say that generally we're looking at global mean air temperature for what we are in CESM, the TAS output. So these are sections of that paper. If you'd like to read and comment on it, I can attach a link, send out a link to all of you. But the main focus, the main thrust of our efforts was to actually define what the long-term temperature trend is. So the Paris Climate Agreement talked about 1.5 degrees in the long-term temperature trend. And so that means we're trying to detect sustained warming on a background of temporary fluctuations. If we imagine that annual global mean surface temperature, global mean air temperature, these are noisy signals compared to in what a climate modeling world would we think about the ensemble average. So on the observational side, we can smooth out the noise temporally instead of looking across different ensemble members. But there's still a challenge there because we have to predict a 20-year centered running mean in the center. So this 20-year window would also include, well, now up to 2036. So again, that's the 20-year centered running mean is the target of what we're trying to obtain. And then there are a bunch of rather straightforward methods that we looked at and rejected. What's often done is to report a lagging mean, but this obviously misses the center of the climate signal because it's warming so fast. We could just draw a trend line, and it matters then whether you start the trend line in a kind of reasonable spot. There's the hinge fit starts in the mid-1970s, and that's often used. And there's also a constant offset that we can use to correct the 10-year lagging mean. But both of those methods aren't robust to potential changes in the future trend, in the future climate trend. So in other words, if we were to actually get on SSP 126 and the climate were to kind of level off, it's obviously not taking a linear trend anymore. So this is our overall evaluation framework. We started with 71 potential candidate methods, and then they went through successive filters or screens. And each time we are comparing them to that gold standard of the 20-year centered running mean. And then ones with root mean squared error above 0.06 for these historical and SSP screens were tossed off. So that got us from 71 methods to 40 methods to 24 methods. And then, so that was with a RMSE constraint of less than 0.06 degrees. Then we used another ensemble of potential volcanic eruptions in the 21st century. And that was a bit messier, so the RMSE screen was relaxed to 0.077. And then there are two potential things that you can do with volcanic eruption. I'll get to this in a second, but you can either say, well, we should include the volcanic eruption signal a little bit to do what the 20-year centered running mean would do. It would bump up just a little bit. Or we might want to ignore it entirely, do what a climate model ensemble average would just completely remove that volcanic signal. And this is the anthropogenic attributable methods. So we're down to 7 and 2. And then we applied these to a record ensemble instead of just using one record like Hadcrut. This is what that looks like. So again, we started with 71 methods and then are constraining them to only have RMSE less than 0.06 degrees. This looks a lot like a ensemble, like a historical 20th century ensemble run, but no, all of these are different methods that are aiming at this black 20-year running mean signal. For this test, we're taking in the Hadcrut 5, applying this 20-year running mean, but all of these methods can't see the next 10 years of that. They're all trying to nowcast this 20-year running mean signal. So again, the next step was to constrain further for robustness to the future carbon dioxide trajectories and potential volcanic eruptions. We used the Max Planck Institute's ESM1, and I'll get to that in a second, but this was just used because there was a readily available ensemble, a large ensemble for each of these SSP scenarios, and I plotted them here. NOR-ESM was used for the volcanic ensemble, and that was just in RCP 45. So this is a very subtle thing about the MPI ESM model that I just want to raise for the modeling folks in this room. And I don't think it's true of CESM, but a lot of these methods, which are trying to extract the 20-year centered running mean to nowcast that signal, are extremely sensitive to changes in forcings or to changes in the climate sensitivity. And so even though the transition from the historical to the future in the kind of raw signal, this is the ensemble average now, looking across all 50 ensemble members from MPI ESM. In blue, it's tricky to see that anything's happening at this switch from historical to future runs. But if you apply that centered 20-year mean smoothing, is that yellow line, and that's actually following something extremely close to a quadratic curve, and it's pretty apparent that it slows down and changes track right at the transition point, and that's true for both SSP 245 and SSP 370. Okay, so jumping ahead to the end, because this is a very short talk. We picked these as the final selected methods. They were generally within 2 years of historical threshold crossings. And as I said before, there are 2 sets of final selected methods based on what do you do when there's a major volcanic eruption. So there's one camp of co-authors who wanted us to do nothing when a method sees a major volcanic eruption. So this is a simulated volcanic eruption, kind of the worst possible case to get really close to crossing 1.5, and then a volcano pulls the centered 20-year running mean just down below it. We could either completely ignore a volcano, that's the attributable methods, or we can try in these methods to correct back to something close to the 20-year running mean, so that the volcanic eruption has an impact, but it's much muted. It's substantially muted compared to the raw signal. I just want to point out, of those selected methods, of those 2 and 7, most of them are climate emulators. So these are showing they're actually perform very similarly when fed in different forcings. And this is a key feature of climate emulators, that they can, unlike what we call statistical methods, they don't just look at the temperature record. We're also feeding in the various different forcings, whether that's greenhouse gases or the natural volcanic fluctuations and solar effects, other anthropogenic aerosols. And those 3 methods are the EBMKF, the energy balance model extended Kalman filter, the global warming index, and FAIR, which is the finite amplitude response kind of Monte Carlo simulations. So again, what are these climate emulators? They're vastly simplified climate models, nothing like CESM in complexity, about 1 billion times faster. They're generally tracking global averages of things. But they're so fast that all of the coefficients can be adjusted every year through data assimilation, and there are a variety of statistical techniques to do that. There are also different dynamical assumptions that you can make about what the climate system actually looks like. Where are there feedbacks? Where are we prescribing forcings? So this is an example of one of those that I developed. This is the EBMKF. And a critical thing that you can see about what it's doing, it takes this in gray, those are the annual reconstructions of global mean surface temperature through HAD-CRUT. It provides a window in light blue of where it expects those to land, but in kind of lime green, there's a much tighter uncertainty about what the climate state actually is. And those are the coefficients that get updated every year. In this particular model, lots of other coefficients about feedbacks and such are fixed, but it can adjust the climate state based on these new observations, quasi-observations. So there were several other methods that weren't climate emulators that also passed. There were these statistical methods, LOIS, GAM with AR1 process, a linear trend Kalman filter, which means it doesn't know anything about the climate. It just assumes that the trend keeps skating in whatever direction it's going. Then there's this current global warming level, which actually does use Earth system model decadal projections. So in other words, you run a decade into the future using climate models and combine that 10-year future, and there's a whole distribution of those with the 10 years of what's happened up to, well, including 2025 for this window. So this is the final step. There isn't just one observational record of global mean surface temperature. There are lots of things besides HAD-CRUT, and these were combined together by my co-authors using a kind of genealogical approach to make sure that sea surface records aren't double counted. That generates this distribution of things, which has both internal and external uncertainty. I did something very similar with the ocean heat content because some of the climate emulators require that. And then these are the final headline results for what the climate is doing in 2024. here are my conclusions. We haven't crossed 1.5 degrees yet. We're approaching it, but we can say with certainty we haven't crossed this threshold yet. And we know that primarily using climate emulators. Any questions?
Questions? I guess I had a question about your conclusion about there being a real sensitivity to the transition of the forcings between historical and SSP. And I wondered if that really is a sensitivity to that transition, or is it just that, I guess I would have thought it's just nonlinearity in the forced signal that means it's kind of following that quadratic fit earlier, and then it transitions into a more linear signal, whether that be because the greenhouse gas force signal is nonlinear, but also the combination of greenhouse gases and aerosols. What makes you think it's really that transition between historical and projection?
So you're right, this could be a number of things. I haven't exactly identified what it is, but so I'm going to pull up a different slide briefly. So in order to deal with that issue, this, well, all of the methods, in order to deal with that issue, we allowed them to be modified slightly, because many of the methods that performed very, very well in this test, in the historical case, all of a sudden missed the boat entirely in all of the SSP projections. And so we allowed modification of those methods. And to deal with that, this energy balance model, we added in a correction term that basically notes, here, I'll share this slide. We added in a correction term that allows there to be some kind of shortwave forcing that isn't accounted for by other feedbacks. And right at the transition, that correction term drops from hovering around, 0 to positive 0.2, and it suddenly goes down to negative 0.4. So the shape of that transition indicates that we are applying a constant top of atmosphere energy flux, although the model didn't also had major problems with the radiative top of atmosphere forcing, MPI ESM. There were other issues with actually obtaining that variable directly and just looking for it, but the inferred shortwave top of atmosphere forcing that's unaccounted for by other things suddenly jumps to around negative 0.03 watts per square meter.
Interesting.
So I hope that answers your question. This is something that is still uncertain. I'm unsure of, but I am very confident that, so this didn't happen in the NOR-ESM model. This was exclusively a problem in these fluctuations in NOR-ESM, in the inferred output. They have to do with kind of second order corrections to the volcanic forcing, where we to better approximate the 20-year mean, the forcings were given just a little bit of an additional kick. There is no dramatic jump down from positive to negative unaccounted for flux in other climate models. This is something that just happened in MPI ESM.
Okay, thanks. We have a couple of questions online that we'll take before we go to the break. So we'll start with Claudia and then Rob.
Yeah, thank you. I'm curious about this issue of considering volcanoes or not, and I'm hoping that it was not an either or, because I can think of, two very different questions that are asked where considering volcanoes or not matter. So if you are interested in attributing warming to greenhouse gas emissions, then you want to avoid volcanoes from
Absolutely.
saving you some degrees, right? Some fraction of a degree. While if you're concerned about adaptation, then you want to consider the reality, which is a cooler climate. Or was there some other subtle, reason for the diatribe?
No, that you summarized it perfectly. That's exactly why we presented kind of two different sets of what the final selected the best group of methods should be. And so they're highlighted in different colors, they're attempting to do different things, and we presented both results.
All right, thank you.
Right now, the realized warming is ever so slightly higher than the attributable warming. That they are different things. They are different objects, but neither of them have definitively crossed 1.5.
Thank you.
And Rob?
Hi, yeah, thanks for the talk. I thought it was just worth mentioning that I've also found something a bit weird with that MPI model at the transition point.
Maybe you found it. That's amazing. Okay,
but on something totally different. So it was with the variance of the divergence of the wind, and there was a complete step change in 2015 as soon as they released the SSP 370 simulations. And I emailed about this, and they didn't really know what was causing it, or didn't seem that interested in looking into it either. So yeah, I just thought I'd mention it.
Okay, so maybe this is an argument that CESM2 should make its own SSP ensemble.
We do have an ensemble of
Large, yeah.
We have 3 scenarios with at least 15 members, but we don't have the 1, 2, 6.
Okay.
But my guess is you're going to see a thing going on there too, because I think the volcanic forcing has a big impact as you transition from the historical to the SSP and CSM.
Okay, great. Well, I look forward then to potentially reapplying it to the CSM's SSP ensemble. Also,
Yeah.
I saw something in chat.
Yeah, I wanted to say about this. This was coming up in an entirely different project, but it may be relevant here. And I don't know if this is the case with this model, but a collaborator raised that if you're looking at ensemble member 1 in the historical, some models on ESGF didn't use that same ensemble member to spawn ensemble member 1 of the projections. So it might just be that you're actually not looking at the same simulation. And I can find more details of this and see if they've identified which models have this problem.
So great. I'd be happy to look into that and investigate that further. If we could match things up better to have a smoother transition, that would be great. I don't know if that was necessarily the issue here, because there were 50 historical simulations, there were 50 future simulations. Even if they got scrambled, on average, we still see this drop. And so I'm not sure that would entirely address the issue, but it might do something. Thank you.
Yeah, you're welcome. I'll try to learn more and follow up.
All right, I think we should. Somehow we're behind time after.
Sorry,
No, thanks. It was very interesting. It's not, yeah. So we'll just take a break now, come back at 10:50. Yeah, right. What we're doing. Yeah, we'll see you there at 10:50. Thanks everyone for the great talks.
Okay.
$40 worth.
Oh, yeah.
Snack.
Yeah, that's right. Bring tailbacks. Like, I don't have a project. It's just like magical. Just
Yeah, well, you could do that. You could pass for this. What did you end up doing?
Nothing was.
Nothing.
So that's why I was like, ended up having.
So,
Yeah, it was a little confusing.
so I wrote that for Nan's, whatever data she used.
Yeah.
I don't
I
remember.
also wasn't sure.
But then that got put on hold when there was questions about, I raised some questions about the data itself, not what I was doing, but the original. Anyway, so 4 components. As of a year ago, Amsterdam for steamerization was working. ICE, I had no idea. And prompt, I have a script. So how about the 4 of us? And then from there, we could decide whether to bring Jim in. So why don't you arrange a meeting?
Okay.
And we'll just keep moving forward.
That's why the new CSM3 has
I was thinking about it. I was like,
cooler.
no, the atmosphere and land.
Yeah, something.
Someone.
Well, who knows? I mean, it's a product of all these changes to the aerosol scheme and the clouds.
Sure. Even next
They put all these
even
changes
now
in.
get
and
ice
give it what you
cream,
get, right?
yeah.
And you should give it acceptable or not. I mean, it's not.
Well, that's, okay, so that's what I don't understand. I thought Jim told you, no, we can't.
Crazy.
Pop doesn't work in his thing. That makes sense because the memorization tool is focused on CSM3.
Also just
Working on that. That makes sense.
Yeah.
But
Could be.
just size 6.
Because mom
is
is
size
the
5.
They are, right? Yeah.
But
Yeah, so it could be.
let's talk immediately about it, and we're all on the same page.
I thought there was.
I'm unmuted now. In this paper, they did a nice summary where they really highlighted this data inconsistency. So these are global land surface temperature averages and ocean surface temperature averages. And basically what this paper is showing is that this evolution of sea surface temperature that get any product off the shelf right now pretty much is just physically implausible. And they pushed for understanding this, correcting this in data records. What is great is over the past 10 or so years, the scientist Duo Chan has been working on doing exactly that. So we knew there was issues with our sea surface temperature records in this period. They're all measured by buckets, and that's a really hard thing to bias correct. And so Duo and this project Descent has been working on correcting this sea surface temperature record. And so you notice in this figure, the red line follows a much more continuous, approximately linear warming throughout the early 20th century, rather than having this cold dip that all of the other products, these gray lines, show. And so this was all great. We had a product that was correcting for some of these biases at least, but the problem was it was not interpolated. And so in the past few months, we now have an interpolated sea surface temperature out of Duo Chan's group. I didn't actually include my figure. What's really nice is that they, instead of just using some sort of crude linear interpolation or stationary Gaussian process kriging, they used some non-stationary spatial methods that actually really did a really good job of capturing local covariance structure. And so you can imagine here a really nice picture of reconstructing penicillin limits from only a few data points.
And so this was really huge because this allows us to ask the question if bias correction of these observed sea surface temperatures improve AMIP simulations of the early 20th century. And so I'm keeping this pretty vague right now because it's early into looking at it, but basically we're now able to rerun our AMIP simulations of this period with this new sea surface temperature data set and understand what is changing about simulations of the atmosphere, particularly over winter. And so to do this, we've set up a parallel CESM experiment alongside the existing GOGA simulations run by this working group. And so the existing simulations were run with ERSST, a NOAA sea surface temperature product, tried and true, been around a while, and 10 members of this had already been run. And so what's new here is we're rerunning this exact configuration with these new sea surface temperatures from descent. Again, 10 members. Thanks to Adam for getting this up yesterday so I could update from 5 to 10. And so all the other configurations of the model is same version of CESM, same resolution. We're currently only running it over 1880 to 1959, but can extend it to present if of interest, and all both on the same comp set. Yeah.
Sorry, do you use the same resolution SST boundary condition?
We do.
Okay.
Yeah, thanks for asking. So for all of these, they're all interpolated to the nominal 1 degree grid. And the effective resolution of both of these is about the same. Just making note that their gridded resolution is slightly different. And they both have the same sea ice evolution as well. And so just to show what we're looking at, I'm now plotting our global mean sea surface temperature data from these two AMIP simulations. And so AMIP, we have no uncertainty. We're given the same ocean forcing to both simulations. And luckily, we see this with no error bars here. For all these figures, I've centered them on an 1880 to 1899 climatology to really dramatize the cooling in ERSST. So for the rest of this talk, ERSST simulations will be in blue and descent will be in gray. And we are seeing this cool bias that was found by Sippel et al., which is good because that's exactly the data they were using to find this. And so I'll be also showing some difference maps like this, just showing that we're looking at differences of over a quarter degree Celsius or Kelvin in about a decade of this period. And we really have about a 30+ year period where there's substantial difference in mean in this. Another thing I want to emphasize is this is kind of a multi-decadal signal, which I haven't gotten to look in yet, but we're having not only a substantial absolute difference, but we have a very different pattern of variability in the global mean. And so where this gets interesting is now we can start to look at the atmosphere. So now I'm plotting the land-only global means out of these same simulations. And now we're getting uncertainties from our 10 numbers. And you see that just flipping back and forth, we're roughly following the same pattern, which is great. The ocean dictating the land warming. And where this becomes interesting, I've now added 2 observational products of land global mean temperature in a dotted line. And very roughly, these new simulations do a much, much better job of capturing what we've actually observed over land. And so this is basically recreating one of the plots in Sebastian's original study, which showed these dashed lines and the blue simulations are wildly inconsistent. Basically, if the ocean has this big multi-decadal cooling, there's no way we could ever see a land surface temperature that looks like this. And so this is really exciting. This is probably the money figure of the day. I'll talk more, but it's really saying like, okay, these simulations are doing a better job of simulating land surface temperatures as they happened in the real world over this period. And so just to put this in other words, these descent AMIP simulations do a much better job of following the trend and variability of what we actually observed over land in these dotted lines. And so another thing we wanted to look into is I've just been showing global mean so far, but there's also presumably some interesting spatial patterns going on. We know a lot of the corrections to this sea surface temperature data were made in the North Pacific and North Atlantic, kind of 2 centers of mid-latitude climate and indices of decadal variability. And so what I'm going to do is just some initial explorations of calculating the difference between these 2 epochs. So my climatological period of 1880 to 1900, difference with this 30-year period from 1905 to 1930 through 1934, just to get a sense of how spatial patterns of some key atmospheric variables are changing. And so to orient you to this figure, I'm taking the difference of the early 20th century minus the late 19th century. And so here you can see that descent has about no change in global mean, maybe a slight warming, but that's not happening spatially homogeneously. So we're seeing warming throughout much of the tropics and cooling in particularly the North Pacific. Whereas in ERSST, this is that cool anomaly. We're seeing cooling basically everywhere. Yeah. And so what we're really interested in looking at the difference of these. And so here, this is again reflecting that descent is warmer just about everywhere than ERSST. So in these figures, green will indicate where descent is warmer and ERSST is warmer in the pink regions. And in that sense, we're in climate model land. We can look at some other interesting variables. And so this next row, I'm plotting surface pressure and the difference between these epochs. And we can see substantial differences in the spatial pattern of surface pressure over these periods. Particularly, we're seeing a change in the Aleutian low, which might have some interesting implications for North American climate. And we're seeing some pretty substantial difference in the Western Pacific that seem to be communicated across the entire tropics. And so we really are seeing evidence for a reorganizing of the circulation, at least to some extent, based off of these simulations. And we can check that in precipitation, and we see mirrored patterns on this enhanced low pressure in the Western Pacific and descent is mirrored by increased precipitation. We are seeing less robust signals in the mid-latitudes as expected with only 10 members. But anywhere that you see non-hatching is where we have 9 out of 10 of our ensemble members agreeing in sign. And so even though these signals are less magnitude, they are significant. So as we get to a scale more appropriate for particularly the Southwest and parts of South America and certainly in equatorial Africa, I'm really interested to see how these changes in sea surface temperature affect our understanding of both force changes and variability in some of these regions. And so just returning to my question, if by its correction of these sea surface temperatures improve our simulations of the early 20th century, it's a resounding yes for global mean annual land temperature. That is pretty clear that we're now doing a better job of capturing those observations. And it's going to be determined how much this matters for variables over land. There are some significant differences in these spatial patterns that become enhanced when I look at certain seasons as well. What the problem I'm running into now is it's really difficult to compare observations of just about anything other than temperature in this period. So trying to come up with clever ways to understand which I trust more. And so I'm happy to take any questions and go back to the big map figure. And thanks for listening.
Any questions for Nathan online? You can raise your hand or post in the chat. So do you not think like precipitation or something over North America, we'd have enough observations to say?
That's the one place we might. It's going to be hard to do a global analysis.
Yeah, maybe sea level pressure in the Northern Hemisphere too.
Yeah.
Yeah, I guess it gets tricky back in there.
Yeah.
Before
I think
1900.
I ran into the problem where my naive first pass of taking a gridded product off the shelf and applying it, it's like, oh, I don't trust these. So
Yeah.
I'm gonna have to become more pointed and clever, I think, too. But yeah, thanks for.
I feel like in the North Atlantic you can trust things, but there's not that much going on there.
No. Steve.
Can you clarify what you said about the stippling? You said 9 out of 10 members share the same sign, but
yeah, so
the members don't have to be matched with each other.
Yeah, so what I did here is yeah, that's a good point, because I took the difference of the first ensemble members, second ensemble members, third ensemble members, and if 9 out of 10 of those agreed, I called it significant. But that's maybe not the most fair way because there's nothing special about ensemble member 1.
Yeah, maybe do bootstrap across members.
Yeah, I should do something a little more clever there.
There's a question in the chat about what is happening in the Southern Pacific, Southern Ocean. Do you see a stronger ACC too?
Sorry, can you say that again?
What is happening in the Southern Pacific, Southern Ocean? Do you see a stronger ACC as well?
I haven't looked at any correlations yet. And I think again that we're running into.
I think he means Antarctic circumpolar color. I think the answer is that these are prescribed SSTs. So you wouldn't be able to see that, but I guess, do you have any thoughts about what this big pattern there in the Southern Ocean?
I don't. My like naive guess is that would be related to a wave train off of the tropical, like the Western tropical Pacific as well, at a similar dynamic response that we're seeing in the ocean low, but my Southern hemisphere is not as good, so I'll pass it off to the expert.
Yeah, I think to like look at the ACC for the question, we would need to run some coupled pacemakers or something, nudging the tropics towards these SSTs so that we can actually look at that. Questions?
Ask a clarification question because I missed the first part. For the ERST and the descent, do you use ERST to force the descent? Oh, okay.
Oh, no. So I can just show you this slide, but they're two different sea surface temperature forcings. And so what you're seeing, and everything else is the same. So what you're seeing in this figure over the oceans is really the difference in the forcing. And over land is the response to those forcings.
All right, thanks.
Yeah, thanks. And so these will be available once for paper submitted if anyone else wants to look at them.
All right, now we have a virtual talk from Dongwan Kim on atmospheric response to various SST forcings, so nonlinearity. There. Yep. Oh, we see your slide.
Can you see my slides?
Yep, looks good.
It looks good. Okay. And can you hear me well?
Yep.
Is my microphone good enough?
Yeah, we can hear you.
Okay, great. Thanks. Hi, everyone. I'm Dongwan Louis Kim, a postdoc from Woods Hole Oceanography Institution. Wish to thanks to my collaborators from Hui and NCAR. So the western boundary current is known to be the region with the strong SST variability, and it's co-located with the atmospheric storm tracks. So the contour here shows the SST climatology, and the color shows the atmospheric storm track, the meridional eddy heat flux. And as we can see in the North Pacific, we do have the Kuroshio-Oyashio extension region, and over the Atlantic region, we do have the Gulf Stream region. Both are co-located with the notable storm tracks. So any changes in the western boundary current SST may influence the storm tracks, and it could shift storm track to ultimately impact the downstream weather and the climate systems. Therefore, it is important for us to have a comprehensive understanding of the Earth's interaction mechanisms to improve the predictability of the downstream weather patterns. One of the interesting characteristics of this Earth's interaction over the western boundary current is that the atmospheric response has a strong asymmetric characteristics. For example, the warm SST over the Kuroshio-Oyashio extension region can induce this kind of prominent the anticyclone over the North Pacific. And if the response were to be linear, we would expect equal and opposite circulation response to an equal and opposite SST forcing, but that's not the case actually. When we force the model with the equal and opposite cold SST anomaly, the response is still anticyclonic response, similar to the response from the warm SST. So this talk is about digging up this where this asymmetry comes from. So we used the NCAR CSM model, especially the variable resolution CAM6. As most of you know, the variable resolution refers to the unstructured mesh grid, where we can change the grid system so that over the target region, we can increase the resolution up to 1/8 degree, whereas keeping the rest of the globe under relatively low resolution of 1 degree to better resolve any small-scale processes in the target region, but we can also save the computational cost by using this kind of approach. The simulation period is 3 months, focusing on the early winter, November to January. The initial conditions were derived from the November 1st data of the ERA5, ranging from 1979 to 2021. Therefore, for each simulation set, there are 43 ensemble members. The boundary condition is also from the reanalysis, the glorious 12 reanalysis, which is a high-resolution ocean reanalysis that has a horizontal resolution of 1/12 degree. In the control simulation, we simply prescribed the monthly climatology of SSTN sea ice. So this is AGCM style simulation. In the perturbation experiments, which we call it as the warm simulation, we impose this positive SST anomaly, which represents the dominant variability over the western boundary current region. And because of the time, I'm not going to spend more time on explaining how we get this, but if you have a question, please just ask me. In the cold simulation, I simply multiply this pattern by -1 and impose that in the simulation. So the response, so the asymmetry is most strong in the January, so we were going to focus on the January response in this talk. The warm and cold response are defined as the deviation from the control. We additionally measured the symmetric and asymmetric component of the response by defining that symmetry is the warm minus cold, whereas the asymmetry indicates the warm plus cold minus the 2 times of the controls. Okay, so I'm going to skip this for now, but it basically represents the SST forcing represents the dominant variability over the western boundary current region. So let's jump into the response. So we're going to focus on the latent heat flux first. In the warm simulation, following the positive SST forcing, we do have the upward or positive latent heat flux from ocean to the atmosphere. Now, in the cold simulation, we do have downward latent heat flux following the cold SST anomaly. And therefore, the symmetric components mostly account for the latent heat flux signal, whereas for the asymmetric components, we almost have 0 asymmetry on the surface latent heat flux. If we look at the vertically averaged latent heating, the warm SST anomaly, intuitively, as expected, produces positive latent heating over the SST forcing region. That's the black box here. Cold SST anomaly produces somewhat negative heating response, but its absolute magnitude is somewhat weaker than that of the warm response. Such that the symmetry components mainly account for the signals, but we do start to see some asymmetric component as well, that there are some positive asymmetric latent heating response. If we look at the omega at 500, the warm SST does produce upward motion or the negative omega. Interestingly, the cold SST simulation also produces somewhat noisy, but still overall upward motion in the SST forcing region. Therefore, in this case, we now start to have a weak symmetry component, but very strong asymmetric components of the omega. And finally, we do see the circulation to be very asymmetric, such that the warm SST produces prominent barotropic anticyclone, Similarly, the cold SST also produces similar barotropic anticyclone, and therefore the symmetric component is almost zero in the North Pacific. Although we do have some signals in the near the Alaska, and the circulation response is really dominated by the asymmetric components. Now, here I brought some of the vertical structure of the responses of omega, large-scale condensational heating, and convective heating. The red line shows the symmetric and asymmetric component of the omega spatially averaged over the SST forcing region. Now, the solid line represents the symmetric components, and the dashed curve is the asymmetric components. We do see some statistically significant symmetric vertical motion, especially in the lower atmosphere. But the asymmetric component of the vertical motion is really strong in the upper level, mainly above 500 hectopascal level. If you look at the latent heating, first one is the convective heating. That's the green line. We do have that. We do have the symmetric component of the convective heating mostly focused in the lower atmosphere again, and almost zero asymmetric components of the convective heating. Similarly, the large-scale condensational heating, we do have the symmetric components mostly focused in the lower atmosphere, but we do see some asymmetric components in the upper atmosphere as well. So all these overall assessments is indicating that the lower atmosphere thermodynamic variables really follows the SST structure, that the latent heat flux or the lower level vertical motions and latent heating are symmetric and mostly linear, whereas the upper level circulation structures are turn out to be quite nonlinear and asymmetric. So then the question is, what is responsible for this anticyclonic response? And studies have shown that the eddy vorticity flux is important for the formation of this blocking-like anticyclone. So following the message from the earlier studies, we've looked at the geopotential high tendency driven by the high-frequency eddy vorticity flux. Here the V indicates the wind vector, especially the rotational wind vector, and subscript H refers to 2 to 8 day bandpass filter, so the high frequency components. Using this equation, we can compute the geopotential height tendency, and if we overlay that with the actual geopotential height response, so the tendency is shown as the color, the contour is the actual response that we saw. In the warm response, we do see that the high-frequency eddy vorticity flux really contribute to the formation of the anticyclone in this case, as well as for the cold case as well, although the center of the strongest tendency and the strongest response are a little bit off in this case. And similarly, the symmetric components and the asymmetric component also agrees pretty well that the asymmetric anticyclonic response is really strongly driven by the high-frequency eddy vorticity flux forcing. So here comes the summary. The warm SST and cold SST induces similar atmospheric circulation response pattern instead of inducing the opposite response. We've looked at where this asymmetry really kicks in. The lower atmosphere response, as intuitively, is actually symmetric and almost linear. It is the upper atmosphere where this asymmetry really starts to kick in. We speculate that the warm SST or the warm anticyclone is actually a little bit stronger and spatially larger, and that's probably due to the additional effect of the enhanced latent heating driven by the warm SST, which has an ability to penetrate into the upper troposphere to curve the atmosphere. But we're not really sure at the moment how the cold SST forcing really triggers the vorticity flux forcing in the upper level, and that's something that we have to look into a little more. I think this kind of asymmetric response was reported in earlier studies using either regional warp simulation or low resolution global model. But studies have also shown that the high resolution simulation is really necessary to have a robust atmospheric response to the Western boundary current forcing. And to my best knowledge, I think this is the first time that we're capturing this asymmetric response using the high resolution climate model simulation. So with all that, I'll take any questions if you have. Thank you.
Thank you. Any questions?
I have a question.
I know, yeah.
Yeah, very interesting. Thank you for that, for the talk. Have you looked at advective processes? I think mostly your analysis here is really nice and it's mostly vertically, you're looking at the vertical structure, but have you looked at advection into the region at all, or is that not important, like from a scale analysis point of view?
You mean like temperature advection?
Yeah, or yeah, or any type of advective like mass continuity or yeah.
Yeah, we haven't looked at any advective components of this. Yeah.
Okay. Thanks. Any other questions? I guess I just wanted to make sure I understand. So both anomalies are giving you the same sign circulation response in the North Pacific. Is that right? Or had you multiplied the cold one by -1 and?
No. Both produces same sign. So the only difference is the sign of the SST forcing. This, yeah.
Okay. So is it obvious? I guess I could see there being asymmetries in like the magnitude of the signal, but is it clear why these asymmetries would happen in such a way that the cold perturbation gives you the same sign signal?
Can you repeat the question? Sorry.
I guess is it clear how, like what you showed about the upper level omega, is it clear that that would give you the same sign signal between the two SST anomalies?
Are you questioning like the connection between horizontal and the omega circulation?
I guess just your argument with those line plots was that there was an asymmetry there.
Right.
And is the like upper level omega signal of the same sign in the cold and the warm anomalies?
Yes, they are producing the same sign. So the warm SST does produce upward motions, so does the cold SST as well, although it's a bit noisy for the cold case. Yeah.
Okay. Huh. All right, thank you.
Thanks. Yes, I think the upper level omega is more about secondary response to the anticyclone, that there is an upward motion in the immediate upstream of the anticyclone, whereas I think the lower atmosphere symmetric response is more of a direct SST influenced response.
Okay. Thanks. There's another question for you in the chat, but maybe you can address that while we move on to the next talk. Thanks for the presentation. So our next talk, I believe, is in person. Okay, yeah. And we have this laptop here if you'd like to use it, or do you already have yours? Okay.
Share my screen. Is it good?
Yep.
Thank you for having me here. Today, I want to show an interpretation of the pacemaker experiments. Here we take the example from the tropical Pacific and Atlantic interaction as an example. And first, I want to acknowledge the important contribution and support from Matt and Antonietta and Manu Di Lorenzo. So first, I want to ask a question. How do we know the impact of a particular ocean domain on the climate system? And it's hard to tell from just statistical methods or observational data. So people use numerical model to conduct experiments by restoring the modeled SST to observation in a specific domain. And outside that domain, the model evolves freely, and then we can compare the modeled response with the observation. And if they are aligned, then we can isolate the impact of that particular forcing we put in the model on the climate system. And this is called the pacemaker experiment. But here we want to ask that, does pacemaker experiment show us the actual impact from that particular domain? There are some rising concerns about the pacemaker experiment, but we first begin with a simple coupled system where we have A and B. There are two one-dimensional variables, and they are described by this linear stochastic model where the coefficient A and D determines the damping rates, and B and C are the coupling strengths. And we can integrate this model forward with the white noise forcing, and we have the time series of A and B, and the lead-lag correlation tell us A and B are mutually affected by construction. And now we wanted to see how A influences B. We can prescribe A in the second equation with a unique realization of A derived from the coupled run. And in this case, we can see the leading correlation from A to B is isolated, but the peak correlation is greater and shift to shorter leads compared to the coupled run. Although this is a very simple system and the dynamics are very sensitive to the choice of coefficients, so we manipulate this system by making the A influence have a stronger influence on B, or B has a faster damping rate. And in this new system, we can prescribe A again, and we can see from the lead-lag correlation map, we can see among those different systems, even though they are different, but when we prescribe A, it actually have consistent but uninterpretable deviation from the coupled run from the peak correlation. So that's kind of motivated us to investigate what is happening when we prescribe SST in the climate system. And moving on to a more realistic system, take an example of the mid-latitude air-sea coupled system. When we prescribe SST in the climate model, despite the atmospheric response aligns pretty well with the observation, but it seems to suggest there are some fundamental change in the system dynamics as the ocean is driving atmosphere, but in reality, the atmosphere drives the ocean. So we wanted to ask, how realistic can pacemaker experiments isolate the impact of the restored forcing? And what are the issues with restoring SST, especially in a coupled system? To answer those questions, we need to enter a system where we know precisely the system dynamics, but normally it's difficult to find that in the dynamical model. So here we use the linear inverse model to construct a coupled system between the tropical Pacific and Atlantic. The advantage of using a limb is that we know the system dynamics precisely. And as you can see from the equation, the diagonal element describes the internal dynamics within each basin, and the off-diagonal element describes the coupling between those two basins. So in observation, El Nino leads the northern tropical Atlantic warming by 6 months, and while the northern tropical Atlantic warming triggers La Nina 8 months later, and this lead-lag correlation is well captured by our limb and suggests that the limb could capture the observed coupling dynamics, and we know them explicitly. And we can integrate this fully coupled limb forward to generate the synthetic data, and here we treat them as the observation. And then we run this model again, but at each step of the integration, we restore the SST to the synthetic data that we generated earlier. So in this case, the dynamics of the restored SST are exactly the same as the pacemaker experiment. So this is a perfect model experiment. And since now we enter the limb world, we know precisely the dynamics in the system and we can modify it. So we remove the coupling from one basin to another, called the partially decoupled simulation. And in principle, this should tell us the true one-way tidal connection dynamics in the limb world. And more importantly, this allows us to evaluate the pacemaker experiment in a consistent limb framework. Here I showed is the Atlantic pacemaker experiment where we restore to the observed Atlantic SST, and it produces a cooling response in the equatorial Pacific in response to the northern tropical Atlantic. And when we compare that with the true response simulated by the partially decoupled simulation, we can see this cooling response in the pacemaker experiment is exaggerated and it shifts to the eastern Pacific. And one possible reason for this disagreement is that in the partially decoupled simulation, the Atlantic is independent of ENSO by construction, but that's not the case in the pacemaker experiment. So we want to remove the ENSO signal from the Atlantic SST, and now we conduct a fully decoupled simulation in a limb, and we use that SST, which is completely independent of ENSO, to run the pacemaker again, and now it produces a cooling response that's closer to the true dynamics. And for the Pacific pacemaker experiment, it shows SST warming in the northern tropical Atlantic, and this aligns with the partially decoupled simulation. And it doesn't really change much when we remove the Atlantic signal from the tropical Pacific SST. However, this is not the case for the extratropical North Atlantic, suggesting that this relationship is also affected by the coupling from the extratropical North Atlantic to the tropical Pacific. So to summarize, in a coupled system, the restored SST in the pacemaker experiments not only reflects the internal variability in that domain, but it also influenced by the pre-existing signal from the unrestored domain, and that could generate unrealistic response or artificial response in the pacemaker experiments. And in the limb, we construct an energy conserving system where the variance tendency in one domain is balanced by three terms. And the first is the internal dynamics, which implicitly captures the thermal and dynamical process that overall acts to damp the system. And this term is primarily balanced by the white noise forcing term, which mimics the fast evolving process that tries to energize the system. And then we can isolate the variance contribution from teleconnection with the other domain. And all three terms adds up together equals to 0, suggesting that this is an energy balanced system. And now let's see, if we do the pacemaker, how does that change the energy balance? So for the Atlantic pacemaker experiment, in the restored domain, we can see that the internal dynamics now actually has a weakened damping effect, especially over the extratropical North Atlantic. And this produces artificial variance in the Atlantic domain, and it has to be dissipated through teleconnection to keep the system in balance. And when we go to the unrestored domain, we can see that the teleconnection now facilitates variance growth in the equatorial Pacific. And this corresponds to an enhanced impact from the Atlantic to the equatorial Pacific. For the Pacific pacemaker experiments, we can see that in the restored domain, the teleconnection term acts to lose variance in the equatorial Pacific, while in the unrestored domain, the teleconnection actually gains variance through teleconnection. And this corresponds to an enhanced impact from the equatorial Pacific to the Atlantic. So the process of restoring modeled SST to observation produces artificial variance in the restored domain, and that could propagate to the unrestored domain through teleconnection. And this would produce artificial response in the pacemaker experiment. Although we do have to notice that reducing the restoring strains could alleviate this problem, but it cannot fully eliminate it. So in conclusion, the pacemaker experiment must be interpreted with caution because the simulated response that you see could be partially influenced by the pre-existing coupled signal. And in our case, the Atlantic pacemaker experiment exaggerates the cooling response in the Eastern Equatorial Pacific, but the impact on the Central Equatorial Pacific may be more robust. And another important issue with the pacemaker experiment is the disruption of the energy balance. And here we show in our limb that's where that is affecting in the pacemaker experiment. Although we do have to notice that in our limb, the white noise forcing is state independent. But when you restore to the SST, it's a new SST state, so the white noise forcing may be subject to change. And this requires explicit heat flux analysis in the pacemaker experiment. And in realistic pacemaker experiment cases, the model dynamics and the observed dynamics are likely different. So we wanted to go to an imperfect model experiment to diagnose how this mismatched dynamics affect the pacemaker results. To do that, we need to mimic the numerical model pacemaker experiment. And here, as I show as a case that we use our limb to train on the CSM1 large ensemble to capture the CSM dynamics. And then we restored it to the observation. And as you can see from the lead-lag correlation here, it's actually well reproduced by our limb pacemaker experiments. And this allows us for further diagnose of this mismatch dynamics problem in the future. Thank you. And any comments are welcome.
Thank you. Any questions?
I have a question. So, from my a lot of new concepts have been introduced here, but from my understanding, LIM is a truncated system. And what is the difference between the pacemaker experiment and the truncated LIM? What's the key message there? Like the difference actually reflect the dynamics that didn't capture by LIM, or what does that mean?
Well, I talk about the limb validation part, like we compare our limb with the observation.
Yeah, you saw the difference.
So yeah, we must say that the limb is not exactly the same as the observation, but as you can see from the lead-lag correlation, it captures most of the dynamics that we see in the observation. So in our case, we treat the limbs like coupled simulation as the observation. But they are not exactly the same as the observation. But it's just here we wanted to conduct a perfect model experiment. So we know the observed dynamics, and we know the pacemaker experiment that has the same dynamics.
Do you have any interpretation for that difference when you show pacemaker minus LIM?
Okay, it's probably here, like this relationship over here. So the restored domain and unrestored domain, that's the energy budget that we see in the pacemaker minus the LIM that's just the original fully coupled LIM, not the pacemaker. So we wanted to see how this system dynamics become different. And the only difference is we do the nudging here.
Any other questions? And I guess philosophically, do you think like, are pacemakers okay if you acknowledge that the atmosphere may have played a role in producing those SSTs, and then you're seeing the pure response to that SSTs without that atmospheric influence? Or do you think like we just shouldn't be doing pacemakers? Or we should be doing limb-based pacemakers?
I know someone in this room.
Yeah, I just walked in.
But I'm more optimistic. So in some case, we could apply that. Like if I wanted to know how ANSO influenced the precipitation somewhere in Mid-East, it's okay because you don't really see that feedback come in.
Yeah.
So it's not like a coupled system. You just see how the precipitation responds to the seas of temperature. So I think in this case, it works perfectly fine. And it's just here we wanted to say that we diagnose all these in the pacemaker. We wanted to say when you interpret those pacemaker experiment results, you should bear in mind some of the caveat that might.
I mean, it's giving you the wrong result. So basically, that's the point here. In a perfect model experiment, you get a result which is not consistent with the dynamics of the system. And we know the dynamics here, so we know how wrong it is. But how do you do that when you don't know what the dynamics is and it's not a perfect model? So there's a whole other set of issues involved in doing relaxations where you're relaxing a model which has one space to nature which has a totally different space. I mean, it's a mid-latitude SST problem again, basically.
Cool. All right. Thanks. Our next speaker is a virtual speaker, I believe, Zhenghe Shuang. Sorry, is that quite right?
No worries. Can you hear me?
Yes, we can hear you.
Okay, let me just share my screen. Okay. Is my screen sharing working? I can't tell.
We don't see your. Oh, it's coming, I think. Yeah, we can see it.
Okay. Awesome. Cool. Okay. So yeah, my name is Zheng He. I am a PhD student at ETH Zurich, and I'm going to be talking to you about tropical circulation variance response to climate change. And just as sort of motivation for why we're interested about this, the reason we're kind of looking at how atmospheric circulation responds is that, for example, it's a strong imprint on how precipitation changes in the future. So, for example, if you look at the top right-hand block here, it shows kind of mean precipitation change, which, as you can see, has a strong sort of regional response, which is a result of the circulation imprint on the overall increase in precipitation due to Clausius Capitalon. But okay, so that's the mean precipitation. But we also know that the precipitation variability responds quite strongly to climate change, shown by the bottom plot here, coming from Pendergrass's 2017 paper. And so kind of the question I'm going to try to answer today is since we understand the mean precipitation, mean circulation changes quite well, how does the variance of circulation respond to climate change? And so just to give you a taste of what I'm going to be talking about, what I'm showing here is the vertical velocity variance change in response to climate change in CSM2 large ensemble in two regions within the tropics, one in East Pacific and one in the West Pacific. I picked out those two regions because they are significant regions where these changes happen, and also because the sign of these changes are opposite in these two regions. And so, for example, in the West Pacific, we can see that this variability kind of increases really strongly, almost by 20% by the end of the century, and rather in the East Pacific, it increases by about 50% by the end of the century. So yeah, so these changes are significant. And so in this presentation, what I'm going to two questions I'm going to try to answer is first, how is this vertical velocity variance changing, both spatially in particular? And second, what are the mechanisms responsible for these changes? And how I'm going to do this is I'm going to look at this in two large ensemble, taking 50 ensemble members with a spruce biomass burning. So most of the plots I'm going to be showing are going to be 100-year difference between the 100-year difference of 30-year means, and finally, all this analysis is done on monthly data. And so just getting started with the first question, how is this variance changing? And what I'm showing here is a zonal mean plot over pressure levels and latitude of the response. In the black contours, I'm showing the historical climatology, and in the colored shading, I'm showing the response to climate change. And as you can see, it's basically decreasing all throughout the troposphere, with perhaps a slight increase just around the equator, especially in the winter months. And secondly, there's a strong increase sort of right around the tropopause region. We think this is partially related to the rising of the tropopause, such that there's kind of circulation variance where there used to not be. However, let's also look at it from a sort of a spatial perspective, where now I'm showing kind of similar plots, but on latitude longitude grid. The top is showing the climatology just to make it easier, and the bottom is the response. So as you can see, this response is well. Actually, let's first start with the climatology. We can see that, as kind of expected, the circulation variance, vertical velocity variability, is maximized in regions where we have a lot of precipitation, a lot of deep convection happening. And in terms of response, we can also again see that over most of the tropics, just with a decrease in variance with climate change. But in the East Pacific, in particular, there's a very strong increase in the variance. So moving on to try to explain why this is the case. The theory I'm going to draw on is something called quasi-equilibrium in the tropics, and that basically states that we can imagine some deep convective system, some deep cloud, there's convection happening, and on the quasi-equilibrium, so on the sort of a longer time scale where sort of the energy between convection and the energy input into the atmospheric column is balanced, we can basically make some equilibrium statements about the energy budget in the tropics. And particularly, I'm going to be focusing on kind of the structure of the atmosphere itself versus the energy input into the atmospheric column. So coming from radiation or coming from the SST changes. And in particular, the two variables I'm going to be looking at is first is the gross mass stability. And kind of intuitively, you can think of gross mass stability as the amount of energy export per unit convective flux within the atmospheric column. And this kind of tells you, well, one, about the efficiency of convection within a particular region in tropics, and second, about essentially how stable the atmosphere is. And so under climate change, it turns out that gross mass stability kind of increases as sort of the tropopause rises and the atmosphere becomes more stable in general. The second quantity I'm going to be looking at is the net energy input. And the net energy input is essentially the net energy input coming from whether the shortwave longwave radiation and the surface sensible heat fluxes, so latent and sensible. Okay, so these are two variables. Now, so I'm not going to actually show the derivation of how I got to this equation, but you can find out more in a preprint I have out. But it's essentially the once you take this theory and make some assumptions about quasi-equilibrium, you can get to this equation where I have the first term is the response, or the fractional change in the circulation variance, and that's related to the fractional change in the NEI variance, so the energy input variance, minus the GMS change, or the mean GMS change. And so, yeah, the circulation response is anti-correlated to how GMS changes, but positively correlated with how NEI variance changes. And so now I'm going to show how does GMS change and how the NEI variance change. So starting with the top panel, where I show how the GMS changes with climate change. You can see that over most of the tropics, it's very much increasing, and that is due to the rising tropopause. However, in the East Pacific, we see this very strong negative signal, and that is coming from sort of a strong low-level moistening of the troposphere, which decreases GMS in that region. And in terms of the NEI, the response is much more varied, as it depends, as it's a combination of many different things changing, whether that be radiation or the surface fluxes. But I'm just going to highlight one thing, which is this strong increase in the East Pacific, and we think that is coming from the strong ENSO variability within that future period. So in particular, that ENSO variability is increasing. That's increasing the NEI variance in that region. And so, kind of putting everything together, I've shown you that this equation, which tells us that the circulation variance is a combination of NEI changes and GMS changes. And so what I'm showing here is kind of testing this theory out. I'm showing you a 2D histogram where I've binned different all the different grid points by sort of how much the NEI variance changes within that grid point and how much the GMS changes with that grid point. And then in the colored shading, I'm showing the average change of the circulation vertical velocity variance within those bins. And on the left-hand side, you can see what the theory kind of tells us what we expect from the theory. In that, on the positive diagonal, you can see that the effects of NEI changes and the GMS changes cancel out. And so we have a close to zero circulation response, while on the off diagonals, we have both of these things kind of working together to make the circulation variance change. On the right-hand plot, I'm showing the DJF, histogram from using the CSM2 large ensemble data. And as you can see, we kind of reproduce most of these features. For example, on the off diagonal, although the diagonal is now a bit steeper, we have low changes in circulation variance. But on the off diagonals, going, for example, to the top left corner, we see a much stronger change in the circulation variability, and on the bottom right, we have a decrease in the circulation variability. And so kind of the main takeaway from this panel is that we need both of these terms to explain what is happening, which is kind of contrary to, for example, for the mean circulation, it turns out that the GMS term really dominates these changes. Yeah, and so just to summarize this, I've shown that the vertical velocity variance decreases most of the troposphere, except in the East Pacific, and that these changes are actually quite significant over the climate change. And second, that both NEI variance and GMS changes are needed to explain the response. Yeah, and so please feel free to see my preprint if for more information and more details on specific mechanisms. And yeah, thank you.
Thanks. Any questions? Yeah, Nathan.
Can you go back one slide, please?
Yeah.
Yeah, great talk. That was super clear. I was wondering if you had looked or had theories on why, as you switch signs of GMS, it seems like you get quite different effects of the NEI on variance, like just looking across the y-axis in the positive side. Do you have any theories on that? Is that just like a smooth transition, or is it discontinuous?
I think there's kind of two things playing into this. One is, well, as I've shown previously, like the sign of GMS really depends on the region, whether it's East or West Pacific. And in those two regions, kind of there's different circulation regimes. And so specifically, this theory kind of really relies on a deep, on deep convection being the primary driver of convection. And so there's some I guess deviations from that assumption in certain regions. But also second, I guess there's also some feedback mechanisms coming into play between the NEI and the GMS. And so you can imagine, let's say a certain region experiences more GMS or has a GMS increasing, so that weakens the circulation variability, which then can feed into the radiative effect by decreasing, for example, the variability coming from clouds. And so some of these things are correlated together.
Cool, thanks, yeah.
Yeah, Matt.
A technical question. I didn't quite catch how the trends were moved.
How did you say the trends, sorry?
Yeah, how the trend was removed.
Right. So the just by taking the ensemble mean. So all of these values have been detrended by removing the ensemble mean. Yeah.
By the ensemble mean.
Yeah, it was all in model world. Yeah.
Yeah.
And I'm sure you said this at the beginning, but is this variance on monthly averages or daily?
These are variances on monthly averages. Yes.
Okay. All right, thanks a lot. We'll move on to the next speaker. That's another virtual talk from Changfei He.
All right, could you see my screen?
Yeah, it's not full screen yet, but we can see it. Yeah, looks good.
Right, great. Yeah, thank you everyone. Thanks for having me. So I'm Chengfei He. So currently I'm an assistant professor in the Northeastern University. Today I'm going to show a big bios related to the global surface temperature in current 6 models, and including the CSM2. And this work is collaborated with people in University of Miami, Lamont, Hui, as well as NYU. And this work is also recently accepted publication in Nature Communications. So to start, I would like to briefly talk about the global mean surface temperature. The left panel is taken from the IPCC report. We can see it shows the climate model rhythm body produced the past global mean surface temperature. It is quite consistent with observation. So the global mean surface temperature is basically the average between the northern hemisphere and the southern hemisphere, and any difference between the two hemispheres are cancelled during the averaging. But if we take a look at the SST trend in the 1950 to 2014, so the model and observation, they are showing dramatic difference. So for the model, the ensemble mean, we can see the model warms much faster in the northern hemisphere compared to the southern hemisphere. But in the real world, in the observation, it is basically the opposite. And the model and the observation difference is in the bottom panel. We do see this bipolar seesaw pattern here. So if we do a global averaging for this model data difference, it is close to 0. And this really confirms that the global mean surface temperature is well simulated in the model. But if we calculate the difference between northern hemisphere and southern hemisphere, then this is a big bias here. So this bias is not only in the ensemble mean, but also in every single ensemble members in SIMA 6, including CSM2. So today, I'm going to focus on two questions. What caused this bias, and what can we learn from this bias? So before diving into these two questions, I would like to show the bias is not just in the surface temperature, but also like in the tropical climate. We first define the IHTC as the inter-hemispheric surface temperature contrast. Basically, it is the SST difference between the northern hemisphere and southern hemisphere. The time series is the green curve here. Like in the model, we see it overall shows an increasing trend and with strong molecular variability. And the ITCZ and the Halley circulation, they are highly correlated with the HTC. And on the right panel, this is from observation. Again, these three curves, they are highly coupled. But for the green curve, the HTC, we see it shows the overall decreasing trend, also with strong molecular variability. So we see here the ITCZ as well as the Halley circulation, they are quite different between the model and observations. As we know, the observation is, just one realization. So it has both internal variability and the external force responses. And the ensemble mean of the SIMA 6 is just force response. So the first hypothesis is that the observation is dominated by internal variability, and the model data difference is just internal variability. One possibility is the AMOC. Any perturbation in the AMOC could lead to a bipolar seesaw pattern in the sea surface temperature. This is hypothesized by some previous studies. And there is another possibility is that the observation is also dominated by external forcings. So the model data difference is due to their sensitivity difference to the forcings. As long as the external forcing is large enough, the difference in the sensitivity to these forcings will translate into different responses in the model simulations and observations. And first, we are able to show the internal variability in SIMA 6 PI control simulations cannot explain this model data difference. So today, I will just focus on the second hypothesis here. To see if the observation is driven by external forcings, we just use very simple multilinear regression. We regress observed IHTC onto the IHTCs in the single forcing simulations. As a result, the IHTC is combined by the different forcings as well as the residual, basically the internal variability. And the beta here is a scaling factor. It is a regression coefficient. You can think this is the sensitivity to like external forcings. But there is also a big problem here. The greenhouse gas and aerosol-induced IHTCs, they are actually highly correlated. So there will be strong collinearity for this more linear regression. So we first disentangle this collinearity between the aerosol and greenhouse gas-induced IHTC before we do the regression. To do this, to disentangle the collinearity, we use the PCA. What I show here on the left panel, it is the IHTC in the aerosol and greenhouse gas rounds. They are highly correlated. And then after PCA, we get two modes. So these two modes are orthogonal, and both of them have physical meanings. So we first focus on the PC2. It is in panel D. So the PC2 is plotted with the linear detrended IHTCs induced by the greenhouse gases and aerosols. So pretty obvious here, the PC2 is dominant by the aerosol forcings. This is the molecular variability dominant by the aerosol forcing. And then naturally, we go to the PC1. It is in panel C. The PC1 is the a nearly linear long-term trend, and it is combined by both aerosol and greenhouse gases. Aerosol shows a negative trend, and the greenhouse gas shows a positive trend. So to summarize here, we see the PC2 is molecular variability dominant by the aerosol, and the PC1 is a long-term trend driven by both aerosol and greenhouse gases. Now we return to the regression. We convert the first regression into the second regression. The IHTC is combined by these two modes as well as natural forcings and the residual internal variability. So here is the result for the second regression. First, we regress the model, we do test regression for the model for the ensemble mean of the CMIX, and its R-squared is 0.97. So this really validates our method because by definition, this is a false response. Then we regress different observations onto different predictors. What do we see here? The R-squared for these regressions, they are all about 0.8. That means a significant portion of the real world is driven by external forcings for this HTC. And then now we are able to compare these regression coefficients to address the model data difference. What we see here for beta PC2 and natural forcings, they are actually quite consistent between the model and observations. But the PC1 is quite different here. So first, for the PC2, so that means this is multi-decadal variability. So this suggests the sensitivity to the aerosol forcing in the model and observation, they are consistent. But for PC1, we can see model is positive and observation is negative. For model, only the greenhouse gas can produce this positive trend. And in the observation, this is driven by the anthropogenic aerosols. So here we see that the model is too sensitive to the greenhouse gases. It is dominated by the greenhouse gas response, but the observation is actually dominated by the aerosols. And in the last slide, we compared ensemble mean with observation, and the model data difference is mainly because of model is dominated by greenhouse gases. We can also compare each model with observation, right? To do so, we reduce the regression for each models. Then we will get a list of beta PC1 and beta PC2. In this figure, what I'm doing here, I'm plot each model's beta PC1 against their ECS. So each number here is a model. So we see like the beta PC1 and the ECS are actually highly correlated. That means the model spread for the HTC trend in this historical period is related to the sensitivity to the greenhouse gases. A model has a higher ECS, it tends to produce a higher HTC trend. And the real world, we can see compare the real world observation with all other models. So all other models shows a higher trend compared to the observation. This again confirms that this is a systematic bias in current climate models. And this may also imply the real world ECS is probably at the lower end of current model predictions because these high ECS models are quite far from the observations. And the physics of this model bias and the model spread is because of the surface wind speed in response to the greenhouse gases. What I'm showing here, the shading is a trend of the surface wind speed, and the contours are the season temperature trend. The solid contour means it is relative warming, and the dashed contour means it is relative cooling. Using the subtropics in the southern hemisphere as an example, so we see here the surface wind speed increase in these regions. That means it will enhance the turbulent heat flux over the ocean surface. It will take away energy from the ocean surface, therefore leads to relative cooling regions. And at the same time, in the opposite, in the northern hemisphere, so when the wind speed reduces, it leads to enhanced warming there. So pretty obvious, the CMIX ensemble mean is dominated by these greenhouse gas responses. These patterns are pretty similar. And I'm also able to understand the intermodal spread for this trend of the HTC. So same thing, we define an inter-hemispheric wind speed contrast. This is the x-axis. This is the trend of the IHWC. And we plot against the IHTC. So in this way, we can see, again, we see a strong linear relationship between these two metrics. That means the majority of the CMIX models are producing a positive trend in the HTC, and they have a negative wind speed contrast between the two hemispheres. This is why the reduce of the wind speed will enhance the warming in the northern hemispheres. And we already explained the beta PC1. So what about beta PC2? So for beta PC2, we can also plot it against the ERF ACI for each model. The ERF ACI is the effective radial forcing due to the aerosol cloud interactions. You can think this is a sensitivity to isopycnic aerosols. We do see here, again, we see a good linear relationship between the beta PC2 and the ERF ACI. That means a larger ERF ACI will tend to produce a larger amplitude of the multi-decadal variability. Physically, it is because if the model is sensitive to the aerosols, in that way, it will cool more in the northern hemisphere. And also, we see that here is the observation is indeed within the model spread. So based on this, we are able to constrain the real-world ERF ACI. So the results is like this. From our study, the ERF ACI for the real world is about 0.6, and its uncertainty is about 0.3. The strength of the ERF ACI compared to the IPCC report is weaker, but we can also see we significantly reduce the uncertainty compared to the IPCC report. Basically, I think we reduced by more than 50%. So here, the take-home message is that for the first question we see, this system bias is because the model is dominated by the greenhouse gases. The model is too sensitive to the greenhouse gases. But we do see that the model and observation are consistent in multi-decadal variability. This is because the model's sensitivity to the aerosol is consistent with observation. And based on this consistency, we are able to constrain the ERF ACI to like 0.6. And the ECS also may be lower at the lower end of the current model predictions. Yeah, that's it. Thank you.
Thank you. Any questions for Changfei? I guess I'm wondering, do you have any thoughts on like how it is that we kind of seem to do okay in the global mean, despite having this big bias in the greenhouse gas forced hemispheric asymmetry? Is it just chance or?
Yeah, I think the problem is really because the global mean is the average between the northern hemisphere and southern hemisphere. So the difference is cancelled out. But for this hemispheric difference, it really emphasizes the difference between the two hemispheres. The common part is cancelled out when we do this difference.
Yeah.
So still, it is quite different. These are two problems.
Yeah, it just seems like the feedbacks are so different between the hemispheres that it's like, I don't know, it just seems fortuitous then that the global mean is kind of okay.
Yeah, to me, so seems like maybe all model centers are tuning their models to fit the global mean surface temperature, but we didn't tune that for like the difference between the two hemispheres or the surface temperature for each hemisphere.
Yeah, I mean, we don't, I wouldn't say we tune to fit to the global mean. We look at the global mean, and if it's like doing something really off, then we worry about it, but not I would say to the details of what you're looking at.
I see.
Yeah, but yeah, it's probably different across centers. Steve?
So in this plot, I'm kind of surprised to see the CMIP ensemble mean not show a strong warming hole in the North Atlantic. And so I'm wondering if that is part of the story, that models aren't simulating strong enough of an AMOC decline.
Yeah, this is a great question. So the CMIP-6, I think, so it is both driven by the aerosol and greenhouse gases. For aerosol rounds, I think there is a strong, the AMOC is intensified, and this overwhelms the reduction in the greenhouse gas rounds as a result. So there is no clear warming hole here. And also the period is what we focusing here is 1950 to 2014. So during this period, there may be some subtle difference here. Like even for the observation, we didn't see a strong warming hole here.
Can I please just extend the discussion for the PC2? It shows a very interesting V-shaped pattern centered around like 1980, and a lot of other variables like Pacific decade oscillation, precipitation, and humidity in some regions. They also show this kind of interesting V-shaped pattern. Do you have any comments? Can I just extend your conclusion saying, okay, aerosol changes cause those changes in PDO, in precipitation, in humidity?
This is a good question. So at least I'm confident to say that the aerosol caused the AMV during the recent past because of the Clean Air Act. The aerosol emission ramps up before 1980, but after 1980, there is a Clean Air Act, so the emission of the aerosol reduces. As a result, it produces more decadal variability in the forcings. So in this way, the surface temperature follows this forcing variability. For moisture and for other variables, maybe true. I haven't tested that. So yeah, this is a good question. It definitely worth to be further explored.
Thank you. So we'll move on to our last talk before lunch, and that's Tong Tong Xu. Do you want to use this laptop or you have?
I can use this.
Okay, cool.
You see?
Yeah, it's not full screen yet, but it looks good.
Full screen. What is full screen on my laptop?
Maybe it was just taking a second.
I had to share the full screen to get it to work.
Yeah, but this is full screen on my laptop already.
Did you just share the PDF?
I can try the PDF version.
Or, oh, sorry, I mean,
Or like I had to share
the
entire
entire
window,
screen, yeah.
not a specific application.
You could also try with this one.
There's some way to like swap because it's seeing the second screen. So
Yeah.
you just swap. What is on your laptop?
Like that. Sorry.
Sorry, I was just trying here.
Is this one?
Oh, that's good, but I'm not sure if it's me that's sharing or you that's sharing. It's me. Do you want to just do it with this
Yeah,
one?
yeah.
Oh, is it? Oh,
You right?
yes, it's me.
Hello everyone, my name is Tong Tong Xu. Today I'm going to talk about sensitivity of Northeast Pacific marine heat waves to seasonality of tropical and North Pacific dynamics. I would like to first acknowledge my co-authors. They are Matt, Shen, Antonietta, Dan, Mike, and Manu. So in this talk, I will cover these three different aspects. First, I will talk about the regional diversities of marine heat waves. Specifically how different regions in the Northeast Pacific can be associated with different ENSO flavors. And then I will talk about seasonal dependence and ocean memories. And finally, over all these aspects, I will talk about the cycle-stationary linear inverse model as a supporting tool that can help us get many more realizations with statistics consistent with the reanalysis that we are looking at. So first, here, what I'm showing are the patterns of ENSO flavors. On the left is the Eastern Pacific ENSO. On the right is the Central Pacific ENSO patterns. And these are defined based on the rotated EOF approach. And what this means is if we take the tropical Pacific SST and then do the EOF analysis, and then take the first two leading principal components and then rotate them based on these equations, and we can get their indexes. And then finally, we can do the regression to get their spatial patterns. So we do this similar analysis, but using the ORAS5 sea surface temperature anomaly dataset. And we get a very similar pattern on the left. This is still Eastern Pacific ENSO. Right-hand side is the Central Pacific ENSO. And if we extend this regression analysis to the North Pacific, then we can see how the Northeast Pacific can exhibit different structures corresponding to different ENSO flavors. For example, if we look at the Eastern Pacific ENSO, then we can see a large area of negative anomalies in the Central North Pacific. But if we look at the Central Pacific ENSO patterns, then we can see that there are a large band of positive anomalies on the coast of US West Coast and also within the Gulf of Alaska. But we can also see kind of like an area of negative anomalies in the Central North Pacific. So this means that, for example, if we sample different regions within the Northeast Pacific, we might get that the marine heat wave in these different regions may be associated with different ENSO flavors. And here I'm showing like 3 different sub-sample regions, and this includes a region for Gulf of Alaska, a region for Central North Pacific, and then a region for Northeast Pacific. Specifically, we can see the Gulf of Alaska region sits in the positive anomaly area, and then the Central North Pacific region sits in at least partly in the negative anomaly region, and whereas this Northeast Pacific region is kind of in the node, like in between of the positive and negative anomaly areas. So we use this 3 regions as like a representative region for our following analysis. And first, what we do is we take the spatially average sea surface temperature anomaly within these 3 different regions to get their indexes. And for marine heat wave, we define it based on, it has to be an event that lasts at least 5 months above 1 standard deviation threshold. And all these events are identified based on the shading, like the bars in the index figure. And the next thing that we want to do is, because we have identified all these marine heat wave events, so we want to project it into the ENSO phase diagram. And by ENSO phase diagram, we mean that this x-axis is the PC1 of tropical Pacific SST, y-axis is PC2 of tropical Pacific SST, and this is kind of like a common diagnostic to show the ENSO flavors. And what we are doing here is we have identified all the marine heat waves, and then we identify that their corresponding PC1 and PC2 values when these marine heat waves are occurring. So different colors here represents one single marine heat wave event, and by one single marine heat wave event, you can see that there are a bunch of same color dots, but they're connected by a black line. So this means that it's one event. And we do this for these 3 different regions. So they're all in this ENSO phase diagram. But you can see that we really don't have many events to kind of summarize their common characteristic based on like different regions. And so what we are using here is a linear inverse model approach. And specifically, this is approach, this is a data-driven stochastic model trained on sea surface temperature anomaly and sea surface height anomaly reanalysis. And we use this to generate many realizations with statistics consistent with the reanalysis, and this is ORAS5. And furthermore, we are using a cyclostationary limb version, and this version can capture the seasonal cycle. So now, with many more realizations, we can get all of the simulated marine heat wave and their associated PC1 and PC2 values, and we plot them all into the same ENSO phase diagram. And now the pattern seems to be more obvious. On the left-hand side, if this is a marine heat wave occurring in the Northeast Pacific, then we can see that it sits in kind of that it has like a relatively Gaussian distribution center close to the origin, with just like kind of like a slight slight shift toward a positive PC2 values. But if we're looking at the Gulf of Alaska, then all these cluster is like along the positive CP axis. And if we're looking at Central North Pacific, they are clustered around the negative PC1. So this kind of indicate that, for example, for marine heat wave occurring in Gulf of Alaska, they may be more associated with CP and CP El Nino. But if it's like a marine heat wave occurring in Central North Pacific, they may be more occurring associated with like the canonical La Nina conditions. And if it's a marine heat wave in the Northeast Pacific, then it might be in this transition, like it's not quite related to ENSO. And so after showing the regional diversity of Northeast Pacific marine heat waves, we next want to show the seasonal variations of Northeast Pacific marine heat waves. So this means that we are still using the one standard deviation 5 months duration as the threshold to identify all of the marine heat wave. And now we look at each marine heat wave, when is their onset season. For example, if the onset season is in spring, then we characterize it as a spring onset event. If it's in summer, then we say it's a summer onset event, so on and so forth. And we do this for all 3 regions and also for both the ORAS5 data set and our psychostationary wind realizations. And the solid bars represents the statistics from ORAS5, and then the hollow bars represents the statistics from the psychostationary wind. And one thing that we notice here is that these long-lasting events tend to really start in winter compared to other seasons. But this is just one definition of marine heat wave, and we can use a different definition, for example, using 2 standard deviation at intensity threshold and then 1 month as the duration threshold. And this is closer to the typical definition the marine heat wave community is using. But if we use this definition, then we can see that marine heat wave tend to really occur in the summer compared to the other seasons. So after showing the seasonal variations of Northeast Pacific marine heat wave, I would like to also kind of hint on the role of ocean memory, seasonal ocean memory, in contributing to a marine heat wave occurrence. This is done by calculating the seasonal autocorrelation of the Northeast Pacific index, just as an example. And here the y-axis is the initial season, the x-axis is the verification season. And what we can see here is, for example, for winter anomalies like the February as the initial condition, then this winter anomaly tend to last longer. But if we're looking at a summer season, the summer conditions tends to decay more rapidly. And another thing that we notice from here is, apart from the general decay of the correlation as the lead time increases, there are some seasons that can lead to an increase of the correlation after some time, and you can see it tends to peak in the kind of like in the winter, and this is an indication of the reemergence process. And so for reemergence process, this can be explained by this figure, and this is a mechanism that kind of explains that the anomalous heat trapped beneath the mist layer can re-emerge at the surface in the following winter. And I'm not going to go into too many details about this because of the time limit, but we did this calculation based on the ORAS5 index, and we also repeat the same analysis based on our psychostationary wind realizations. And overall, we can see that they seem to be like consistent, both like the longer memory in winter and the shorter memory in summer, as well as the reemergence structure. But this reemergence structure in the psychostationary wind tend to be slightly weaker. And finally, we would like to highlight again that our psychostationary wind is constructed from both the sea surface temperature anomaly field and then the sea surface height anomaly field. And this is very important because if we do like a psychostationary wind constructed from sea surface temperature, then the structure that's kind of representing the reemergence is like almost just wrong, because these gray dots in the figure represents where the cyclostationary limb realization is significantly different from the ORAS5 patterns, and we can see that the whole structure representing the reemergence is just where the cyclostationary limb is not doing well by just constructed from C surface temperature. And I think that's all for today. So what I'm showing here today is the Northeast Pacific marine heat wave can occur year-round, but these winter onset event tends to be more frequent. And then we also shown that different regions of Northeast Pacific are associated with different types of ensotel connections. And the last thing is the seasonal ocean memory, including the reemergence like behavior, can contribute to maybe wintertime persistence and reoccurrence of marine heat wave in the winter. And we actually later on we actually used like the cyclostationary limb to do more diagnostics, kind of like doing the coupling experiment to see how much exactly the tropical Pacific is contributing to the marine heat wave in the Northeast Pacific, and also like the seasonal memories role in contributing to the Northeast Pacific marine heat wave. But because of the time limit, I would just stop here, and I would love to talk more if you are interested. Thank you.
Thank you. Any questions?
Yeah, this was a really nice talk. It was very clear. Thank you. I may have missed this, so I apologize. But when you were defining your marine heat waves, when you're using that standard deviation, are you using like a moving standard deviation or a static one? Like, because the baseline may be changing as between the beginning of your time period and the end of your.
We are using a constant as a definition, but because we already removed the climatology, so you can think that that definition is implicitly incorporated into the constant standard deviation.
So the climatology you removed was for the whole period.
The whole period.
Okay.
So it's basically deseasonalized but not detrended, is right?
That's what I'm after.
Also being removed.
Oh, the trend's also removed.
Yes.
Okay.
But some of the variance changes from the nonlinear trend, and that is removed.
Okay. Yeah, you see what I'm after here is like.
Yeah, no, that was a previous paper she wrote, basically. It was basically that if you look at variance changes in a lot of these marine heat wave hotspots, if you just take out a linear trend, then the nonlinear part of the trend changes the variance. So you have to remove that as well. And then the changes in variance are generally pretty small, pretty much everywhere around the globe.
Yeah.
So that's part of it. That was.
I missed that. I'll have to read the paper. Okay, thank you.
I have a very subtle question. So how is the NEPAC index constructed? Does that only use SST or?
NEPAC index, it's just SST.
Then it triggers the question why in all places you can see the emergence, but in the cyclostationary limb, can you use SST only?
I think
so. Because in our AS5, in the SST field, you can see the emergence mechanism. However, in the SST only cyclostationary limb, you cannot see it. Interpretation about it?
Well, how I think about this is because the observed field has already implicitly incorporated everything. But if I construct a model based on just the SST, you can see a little bit. I mean, it's not like it's just disappeared totally, but it's not like a reasonable fit to the observation anymore. And with the sea surface height field, I don't know if this makes sense. With the sea surface height field, we consider it as like a upper ocean heat content proxy. So with that help, with that explicitly included, it seems to be helping us to get a more reasonable structure.
Okay, thanks.
Thank you for the question.
Right, if there's no more questions, or did you have a question?
I'm just trying to understand how you can identify that as reemergence as opposed to, you know, multi-year La Nina, or just like, how do you distinguish the process here from just an autocorrelation or a correlation that's coming from ENSO itself?
So what I am thinking is, what we're doing here is we did not extract the time when there is ENSO. So we were just using all of the anomalies, and we calculate the autocorrelation between one season and its subsequent season. So it should include everything, and probably not, as you said, it's probably not just ocean memory. It could be related to ENSO, but this is just a correlation calculation, so it might implicitly include a lot of things. But why we consider this it's like a likely reemergence process is because of the timing of this structure that shows up. I feel like if it's ENSO, then maybe I'm not sure if this makes sense. Maybe it should show up throughout all the seasons, but this is like just the springtime anomalies leading to wintertime increase of correlation. So maybe this is part of the reemergence process, but you're right, it's not 100%, like we cannot say it's 100% reemergence. And even like the ENSO teleconnection, in what I'm thinking is ENSO teleconnection may affect the atmosphere in the Northeast Pacific, and that might affect the mixed layered heat content, and then it might also become some sort of the heat anomaly trapped beneath the mixed layer, and then that reemerge in the winter. So this are all kind of incorporated together. That's why we later on do like the decoupling experiment using the cyclostation link to try to separate them more completely. So I don't know if this answers the question.
It's the node of the ENSO pattern. So the Northeast Pacific, where she's picked, is on the node of the ENSO.
Yeah, right.
So the question, I guess, is how are you getting a 2-year ENSO driving a strong anomaly there solely through ENSO and not through Northeast Pacific mixed layer dynamics, which, you know, you can also reproduce pretty easily in a totally un-ENSO model. You can still get reemergence just fine.
Yeah, I mean, that's the question though. I mean, because reemergence implies just kind of local processes.
But that is, she's looking just at the Northeast Pacific box there. You can have, I mean, she can decouple the tropics and you can see how much of this kind of behavior is from ENSO, and then, yeah, it depends on where you're located. I mean, obviously in the PDO sense, it's getting read by the reemergence, but in that particular location, it's a good area to test it somewhat independently.
Yeah, thanks.
All right, thank you. So that's the end of the climate variability and change working group, and we'll join again after lunch at 1:30 for the Earth System Prediction Working Group session. Let's thank all the speakers again. See you in an hour's time.